Alright, hi everyone, welcome to the Zig 2026 course. So first, what is Zig? So Zig is a systems programming language looking to replace C as the go-to language for systems programming. Features: no hidden control flow, no hidden allocations, and no preprocessor and no macros. So who is Zig for? So Zig is for people who like explicit code and need high levels of performance and safety. The Zig compiler is very strict and will check a lot of your code. For example, all local variables need to be used. Mutability rules are strict. Immutable versus mutable. Return values can't be ignored, unless explicitly. So Zig can be difficult for beginners. So the difficulty I would put, say if Python is like right at the end and C++ and Rust are at the other end, it's somewhere in the middle. So it's a bit harder than C, but not as hard as C++ or Rust. So it's in the middle somewhere. So it's relatively difficult, but not too difficult. So this tutorial will presume you know the basics of programming. So I'm not going to explain what an if statement is. I'm not going to explain what a for loop is. I'm not going to explain what an integer is. I'm going to presume you know that and just tell you what the basics are of Zig. And the last question, isn't it too early to learn Zig? So Zig hasn't reached 1.0 yet. It's 0.15.2 at the moment. Isn't it too early? Well, some things in Zig change. For example, names in the build system. The general purpose allocator was renamed to the debug allocator. The way to get console input and output has changed recently. However, the basics of the language don't change, or haven't changed. So how to create variables, allocator mechanics, control flow, if, for, while, types, so errors, structs, enums, unions, integers, slices, functions, they haven't changed. For example, I created a tutorial project for Zig 2 years ago, and I recently updated it. And the only things I needed to change to fix errors were removing tabs from comments, changing the way to get console input and output, and renaming general purpose allocator to debug allocator. Except for that, everything else worked and everything else was valid, and everything in my tutorial 2 years ago still works, except for some names. So some things might change in the future, but the basics and core of the language haven't ever changed. So before we get started, this video is sponsored by myself. Have you ever wanted to learn chess? Well, why not try Chess Tools? With over 70 tutorials for complete beginners, over 200 interactive master games with some of the game's greatest players, learn about chess history and improve tactically, with 2D and 3D boards with different 3D piece styles, with an analysis board, and tools like Show Attack Pieces, Show King Attacks. Chess Tools is available on Steam now. Okay, let's first start with downloading Zig. So you pick the operating system that is compatible with yours. So I'm going to get 8664. And when you download that zip file, you basically create a folder and drag that contents to that folder. And then you want to go to, I'm not sure how to do this on other operating systems, but on Windows, you have to go to environmental variables. So we go to environmental variables, click this, and we find path, double click path, and then we add a new one and we add Zig. I've already added Zig here, so Zig works. And then what you basically want it to be able to be runnable from any control panel. So you want to be able to type Zig, and it should come up with this. And then the version we're going to be using is 0.15.2. Okay. So there is the master version. The master version is normally like the latest version that isn't completely bug tested yet. So you normally want to get the second to master. You want to get the one below master is the most reliable. Okay, so in VS Code, you'll need two extensions. Well, I recommend getting two extensions anyway. So first is obviously this Zig language, which is the ZLS, Z language support. So the problem with Z language support is it's very good for things like goto and hints, and it gives you basic errors. But it doesn't give you all errors, and for that I recommend my extension, Zig Compiler Diagnostics, which basically on save will show you errors that Zig language won't. Because it will run the code without actually creating an exe and see if it'll find all errors. Otherwise you won't get full error checking. That's really all you need. You don't necessarily need Compiler Diagnostics, but you definitely need ZLS for this. Alright, and then we can get started. So in my previous tutorial, I did actually use Notepad++. I'm going to use VS Code in this situation. The reason I was using Notepad++ for that tutorial was because I I was actually learning Zig on a not very powerful laptop, and using VS Code was actually pretty laggy, so I used Notepad++ for performance, and I just thought, oh, why not, make the tutorial using it, because I've used it the whole time while learning Zig, so that's basically why I was using Notepad++. Okay, we're going to get into the build system a bit later, because it is probably, it seems really complicated, the build system, but you don't actually need it for most situations. Unless you want to build some kind of really big project and you need caching and things like that. So create any kind of folder you want. I'm going to just call this Zig 2026, and we're going to create new text document and call it main.zig. And then we're going to go into VS Code, we're going to open this folder. Okay, so we open this folder. So we have a blank document, completely blank. Let's zoom in so you can see everything. Get rid of this, make this smaller. Alright, so the first thing you normally want to do in basically every Zig file is to import std. So const std equals @import std. Why are we using that? So we can use standard library functions. I'll explain this a bit later. So then we need a function, because we need a main function. We're going to write fn main. And we need a return type, so we're going to write void, like so. And the problem with doing this is we're going to get an error, and I'll show you the error now by saving. Well, we should get an error anyway. Yeah, we go. It doesn't actually say where. Error. Main is not marked as public. So it needs to be marked as public just because every file in Zig will become a struct. So to access the file from outside another struct, you need it to be public. So we need to make main public, and that's how you make it public. You just pub. So public function main, and it returns void. And then let's say, for example, let's create a hello world program, so we can save it now. So the way my Zig compiler diagnostics work is it's on save. So I hit save, and it will get rid of the errors, or it won't. It should get rid of the errors, but it's not for some reason. The reason it's not is because it's std. That's one of my compiler diagnostic problems. I need to, when it's marked std, I need to not actually show the errors, otherwise they will actually show forever. But that's something I can fix later. Anyway, so std.debug.print. This is the basic way to print. I'll explain a lot of this afterwards. So, and then we can write hello world. And then we say if we want to run this. So the simplest way, what I normally do, is I go into the folder. On Windows, you hold Shift, right-click, and open PowerShell window here. That is probably the simplest way just to get something to open here. And then we write zig run main.zig. And for some reason it takes a long time. So it links, and then we go hello world. As we got a hello world project. And that's basically it. There is another way to do it. You can write here and type cmd, and that will create a cmd here, and then you can go zig run main.zig. Does the same thing, hello world. Alright, so that's kind of the basics of how to run. So first I'll explain this. So printing in Zig can be a bit complicated because they have actually updated the interface for printing recently. But the simplest way to print is std.debug.print. And if we actually go to this file, it does actually normally return an error, but it kind of ignores it. It says catch return. I'll explain errors later. But the simplest way to print is to use std.debug.print. Alright, so I thought I'd just clarify here. So you don't want to use std.debug.print for actual real output in like production code and things like this, because this will use std error, which is not supposed to be used for general output. You're supposed to use std output, std out for that. There are other options which I go into later. I go into standard output. There's also logging, which I'll just look for the log section and the standard output section. But for simplicity, I'm going to use std.debug.print just for showing you things, but you shouldn't use it for production code. Then what it takes in is a string, which there is no string type in Zig. I'll get into the types a bit later. But we have a string literal, and then we have a tuple, which is like any type. But basically, it's a way to, you can pass variables to this if you want using this. You put a variable here, so you can put 10 here. and this will print 10. Or you can print multiple variables. You can put 10, 20, 30, and then we can put here, here, here. So whatever you put in here will get printed. I'll show you this. So hello world, 10, 20, 30. So this is basically the way to print. It's like printf in C, for example. You put in multiple args and it depends on the length. But if you do something like this, you will get an error. You say error, too few arguments. Like this, too few arguments. And the problem with Zig is it doesn't actually, maybe in the future they'll fix this, but it doesn't actually show you where this calls. So that is a problem. So you have to kind of be careful whenever you call print without not enough functions. So the problem with my language server is it will not go away because it's now, it doesn't get rid of STD stuff. I don't know why. I have to fix that, but it doesn't matter. We can just restart VS Code to fix that. So restart VS Code, save it, and then they're gone. All right. So that's the basics of printing. You could also make a helper function if you want. So if you want to make a helper function, go fn. Oh, so there you just want print string, right? So I'm going to go into the types a bit later, but say you could go input const u8, and then just call std.debug.print with input and put nothing. And then we could just call here print string and get rid of that. That's just a simple helper function if you don't want to print the arguments. But you know, it's not Comptime. Okay, you'll make it Comptime then. Yeah, I'll go through Comptime a bit later. Anyway, that's a helper function if you really want it. But I'm just going to write in this tutorial. I'm going to write the actual arguments. All right, let's get into a few things. Let's say, for example, we want to make like an add function. So we're going to again write fn add, and we're going to make this an i32. So then we're going to give it some input. So A, i32, B, i32. So we're going to go add 10 plus 10, like this, and then save. And why are we getting an error? So error, value of type i32 ignored. Why is this? It's because Zig is very strict about return type. So here we're calling a function with a return type and we're ignoring it. So what you generally want to do is go const, let's say result, i32 equals this. This is how to declare a variable, and then we can print it. We could just type in print, type in result, new line, and then result, like this, and then the error should go away. So we have const is a way to make it, obviously it's a const variable, you can't mutate it. If you want to make it mutable, you make it var. But doing this will, again, give us another error because we haven't mutated it. Because Zig is very strict. If you create a mutable variable, it makes sure you mutate it. Otherwise, it will force you to make it const. You can also use inferred types if you want in Zig. So you could delete the i32 and just infer that it's an i32. I absolutely hate inferred types and always write it most of the time. The only time I don't really write it is when you got stuff like this, because std is, you know, it's a type. What do I write? Type here? Like, no, it's not really necessary. Or sometimes you can also create aliases like this. You can go const print equals std.debug.print, like this. And if you look at the type of this, this is a const fn comptime. It's like I'm going to write this. Like I'm going to write this as a type. I'm just not going to write this. So when I import stuff, I don't write the name. But if it's like a simple type, like i32, then I'll always write the type, just because I don't like it otherwise. All right. So here, if you want to ignore the return value, you do this underscore this, and then we can comment this out. And that will call the function without really ignoring the return value and not give you an error. Let's say if we run this with the i32, so if we run this, result 20. Okay, there we go. We've called a function, we've printed the result. Okay, let's go through the integer types. First, I'm going to open my tutorial project, which is in the description if you want to run it, if you want to see what that's like. We put that on this line. Alright, so we have variable syntax. So we have const number i32 equals 10, makes a const variable with a 32 bits and it sets it to 10. Var number i32 equals 15, makes a mutable variable with 32 bits and sets it to 15. Types are optional if the type is const. So in some situations, I'm not actually sure what the rule is, to be honest. If you make it a mutable variable, say something like this, let's say make it var, and we're going to print it, and then we're going to change it here, result equals add 20 and 20, semicolon. You do need semicolons in Zig. Let's do this again. And let's see if we take the i32 away. Will it give us an error? It will not. So there are some situations where it will give you an error. I'm not sure exactly what that is. Maybe when it's not obvious. But we'll say if you write something like this. Say if you write 10. Like this. This will give you an error because 10... The compiler doesn't know what 10 is. What size is it? Is it 32 bits, 64 bits? And because this will be on the stack, this will be a stack variable, it doesn't know. So here you have to specify if it's ambiguous. But if you say call add, like we did before, add tells it it's an i32, so it's 32 bits and it's signed, so the compiler knows, so it can infer it. So you need to write the type if it's, you know, something like an integer literal and not known. Or if you do something like this. If you want to not set a type or set a value, you say undefined. This will give you another error because it doesn't know what it is. So you have to say i32 define, undefined, like so. This will probably give us an error if we do this as well, because we're using an undefined variable. No, it actually uses uninitialized variables. Okay, so undefined is a way to use uninitialized variables. So yeah, it won't actually give us an error, but it'll be undefined and it'll be basically stack memory, which will be garbage. So generally, I think set it to 0. Anyway, so back to the types. Array syntax. Do I have the types here? I think I do somewhere. Yeah, so basically we have all the types here. So we have number i8, u8, 16. So what the number means is the number of bits. I'm not going to go too into like the explanation of how bits work, but it basically affects the value. Okay, so we have I or u, and then we have the number of bits. So it actually is arbitrary. You can actually select as many bits as you want. So you could do something like U5, which would be 5 bits unsigned, or I5, which is 5 bits signed. You can do whatever you want. The max, I think, is 256. I think is the max. So you go U256, which is a ridiculously high number, and it's really unnecessary. You normally don't need that. That's most of these. Then we do have a U size. So a U size is very similar to a size T in C or C++, which basically means it depends on the architecture. So if 32-bit, it's 32 bits. If 64-bit, 64 bits. It's basically the size of a register. The register is basically a memory address inside a CPU. It's register sized, and it depends on that. What is U size used for? It's generally used for sizes and indexes if you have arrays and things like that. So if you get like the size of an array, I'll go through arrays later, but if you get the size of an array, U size will be the default. So that's all for integers. Then we have floats. So floats are basically F32 or F64, which is the equivalent of float or double in C. Float and double in C, it's basically float, it's 32 bits, float is 64 bits. And the bits basically increase the accuracy. So F32 is less accurate than F64 because there's less bits. Then we have bool, standard bool, true or false. I believe that's 1 byte, so 8 bits in size. And then we have the string type, which Zig doesn't really have a string type. It has what are called slices. We have slices, which is a pointer and a length. So I'm going to presume you know what a pointer is, but I'll explain it just in case you don't know. So a pointer is a variable that contains a memory address of another variable. So this contains the memory address of the first element, and then the length, which is actually a similar thing to how an array works. But a slice is basically, it's a pointer to another array, whereas an array is actually holding the data itself, if that makes sense. But they're very similar. So arrays are very similar to slices. But we'll go through that later. But what we do for a string type, strings, we have slice. We have this, which is normally used for arrays, but it's actually used for slices in Zig. U8. So this is a mutable slice, meaning you can change the values. And then we also have an immutable slice, which is used with const U8, which is immutable slice, meaning you can't change the values. So I'll show you making some of these. So let's make, for example, we're going to get errors probably. Get used to getting errors, by the way, because Zig is full of them. So say, for example, we make const condition bool equals true. And we got an unused local constant, of course, because Zig is very strict. Let's write print again. Let's say condition let's run this. Have it take ages. Condition equals true. There we go. So that we will actually print out true, because if you're using like say C or something, it would just print 1 and you have to specify. So the good thing about Zig, you don't need to specify what the actual thing is. And we're actually using the alias now, because we've aliased it. We don't need to write std debug.print, but it could be ambiguous in some situations. So you could call it something like std print, just to make it not ambiguous. So std print. Or you could call it debug print. I don't know, whatever you want to call it. I think I'll call it debug print. That's what it is. So the general style guide in Zig is pretty simple. Normally things take camel case. So most local variables take snake case. If it's a constant, something like this, const value equals 10. Then it's uppercase, all uppercase with the underscores. Value example. If it's a function, then it takes camel case. So the first is a lowercase, and the last add example, a word. So it's camel case for function names. That's why I'm using this. And if it's like a struct or an enum, then you use Pascal case. That's the general rules with Zig. All right, so yeah, we have a const u8 slice. Let's write one of those. So we go say const slice equals const u8 slice equals a string literal. String literal here. And let's create this, and I'll show you another error. So we write comma slice. If this does get too long, what you can do as well, you can do this. You can put it on the next line and do something like that. And we're going to get an error here. And it's going to be in writer, which is going to be annoying. But we haven't specified. So when it's something like a slice, because a slice is a pointer. It's not like, a bool or an integer. It's a pointer with a length. So you need to kind of tell the compiler when it's this. So you could write any. I wouldn't recommend using any. That will work, but I believe it will print out in a weird way. See what is it? Yeah, if you write any, it will literally write the characters, which I wouldn't recommend using any. So what you want to write is S. S means slice, and then that will actually print the values and print the letters. So true string literal here, and you could also make it more specific, doing this. So we know when it ends, starts and ends. So condition true, string literal here. All right, let's say I make a usize as well. So I can show you usize by getting the length. So we can go slice length usize equals slice.len. Len standing for length. And we can type in length of slice like this, and go slice length. So if you do want to ignore a variable, like, because it does get annoying when, say, if you just, your const a equals undefined, it will say, oh, unused local variable, just leave me alone, just go underscore equals a, and it will shut up. That's the way to do it. Also with parameters, say if you don't use any of these parameters, so if you make another parameter like c, i32, and you don't use it, it's going to give you an error, so you got to go underscore equals c, and then the compiler will leave you alone. Because get used to the compiler bullying you. Let's print this. So you see here, the length of slice is 19, string literal here. All right. I believe that's all the primitive types that I've gone through. I'm not sure I'm missing anything. You can make a slice of literally anything. So you can make, for example, so I can show you arrays actually. The difference between arrays and slices is not much actually in syntax. So array syntax. So you use the square brackets again, but instead of that, you write either underscore, which basically means you're going to infer the size, or you write the number, and that will make it an array. And then you write something like, I don't know, say i32. So the standard way to make say array like this. What I like to do is I don't like inferred types. You can just do this, and then because what you need to do is actually write the name next to it, and do 1, 2, 3, 4, 5. So you have to write the type next to it, and this will be inferred as an i32. So it should be this. Sorry. So you specify. You got to specify the length or make it inferred, and then again it's not using array. So we are going to write here. I'm not sure if you need, I'm pretty sure you do. Let's see, array. Do you need any if you write array? Yeah, you do. So we're going to write any, and this should print out the array. Which is actually pretty useful to get it to just print the array whenever you want. So here, array, 1, 2, 3, 4, 5. So it prints the actual name. So you don't even need to loop it, which is useful. Right, so that's, you could do this, but what I prefer to do is do this, underscore it, i32, and then we could just put dot. And that's exactly the same. Enable to infer array size. Okay, apparently we're not supposed to do that. Okay, you can't infer the array size here. You gotta say 5. All right. That's generally what I prefer to do. If you actually know the size, because I like to see the type here, not there. Anyway, but you can choose either way. So you can do it that way. You can do it this way, or you can do it that way. It's your choice. But you do have to write something here. You can't do this. It won't work. It's like, what's this? It doesn't know what that is. So you've got to write something like this. So there's our array, and then we can create a slice out of that if we want. So we can go array slice. Oh, this has to be const, right? See, it's very strict, Zig. So this is how, because this is a const, it's very strict with const mutability. So if you have const here, we can't not make this a const. It's going to give you an error. We need to make this a const slice, like that. And what this does is basically it will say 0. So here, you can also make it any if you want. I'll just show you printing this. We got an error. Why? Value. Maybe we should make it any. Okay. So if you put in S, it's actually expecting. It's expecting a. It's expecting U8. It's expecting chars. So I'll show you specifying. So you could start at 1, index 1, and go to the end. And that will go 2, 3, 4, 5. So slice is basically it's a pointer to the first element. I mean, arrays and slices are actually very similar things in principle of what they actually are, because they're both pointers with lengths. It's just that this kind of owns the memory, whereas this is more of a reference to the memory. Because you can't just like create a slice not pointing to something. It has to point to something. But they are pointers as well. Which means, say for example, we make this var, right? We make this var, meaning it's mutable. and then we make this var, we'll just make it like this, then we can actually change the value. So for example, array slice by 0 equals 5. Get rid of that. There's no actual errors. Run this. So what we've done now is we've changed the value 15345 because it is a pointer. A slice is a pointer with a length. So when you're pointing to the second memory address here, and then you're changing the value. So that's when you make it mutable. The const here basically means, it's similar with pointers. So if I create a pointer like this, let's say const, I don't know, say pointer equals a pointer to an i32 equals at array 0. And we're not using it, but we can do pointer.dereference equals, say, 0. I don't know. So now we're changing this value. And this will now be 05345 because we've changed the value. I mean, a slice is basically the same thing. It's a type of pointer, but it has a length. It's basically, if I understand, I haven't shown you structs yet, but go const slice equals struct. It's basically, so it's generic. So we can also make it, it's generic, but I won't write it here. So the value would be, say, pointer is t, so whatever the type is, and then the len is usize. That's basically what a slice is. It's a pointer to a value with a length. That's what a slice actually is. And because it's a pointer, you can change the values like this. So what const here means is you can change what it points to. Same thing with this pointer. So if I create here const num, say example, i32 equals 10. So I could make this var, get another error because we're not mutating it, and then we can set the value of that to @example, and then we can change the value of pointer again to equal 20, and then we're changing the value of example, and it's const, so we can't do that, so we're going to make this var. See, it's very strict, Zig. It's like if this is const, you've got to make sure the pointer is const. But if you want to make this, you can make the pointer const by doing this. Now this will give you another error because we're mutating it. If the pointer is const, you can't change the original value. If this is const, then you can't change what it points to, if that makes sense. So you do kind of need to understand pointers a bit to understand Zig, because a slice is a pointer. You have to understand this. And that's pointers, and it just shows also that Zig is very, very strict with these things. All right, I hope that makes sense. I think that's most of the time, so I can't think of anything else I've missed. All right, so I realise I forgot. So what a char actually is. So a slice, for example, you have const slice const u8 equals hello. What this is a collection of u8s. So a u8, let's say letter, is a u8, which is basically the equivalent of a char. And it will be basically seen as a char. It's basically a number that represents a letter. It doesn't always need to represent a letter, but it's basically a number. So say you could say 65, like this. And then you could say debug print. So here it prints letter 65. So it's 65. What happens if you wanted to print the actual letter? Well, we write C. We can also do both. So we can do this, letter, right, in this part, sorry, letter, say value, this. So now this should print A, if I know my ASCII codes right. Yeah, capital A. Right, so that's basically what a char is. It's a U8. They're exactly the same thing because they basically represent ASCII keys. I'm not sure if there's a way of letting Zig represent Unicode and things like this. I'm not sure if there is a way of doing that. I haven't seen any tutorials explain that, so I don't know. But generally it's an ASCII code, so U8, because it's 0 to 205, which represent ASCII codes. And you can also, if you want a slice, you can also have it, for example, we've got like this. Let's create an array, char array, say chars. U8. Let's say it's like, I don't know, say 5 and make it represent hello. We go dot H E L. I can't goddamn type any goddamn thing. O. And then what we can do is slice can be at chars. You can make it immutable if you want. You can make it mutable if you want, like this. And then you can go this slice 0 equals, I don't know, lowercase h, or something like this. And then we can just print out slice s with a new line, slice, and then print that. It doesn't work at chars. Why? Because it's const, so we need to make this var. Again, the Zig is very strict. So this prints out hello. It's basically the same, but it's lowercase, obviously, because we've edited it. And if we make this const, obviously you can't edit it. It gives you an error here, so we're going to get rid of that line. And then it will print out hello uppercase. So yeah, that's basically all I forgot to remember. Basically, a char is a U8, and you use C to print it as a letter, or you use nothing to print it as an integer. Alright, so I just did some research on how Unicode actually works. Apparently Zig does support Unicode, so we can say Chinese hello is, again, a const U8 slice equals this. And then we can print this out. Let's say Chinese with this. But I can show you the length. If I can actually print the length, it'll be useful. And we might see something quite interesting here. Alright, so I just went down a pretty big rabbit hole trying to get this to work on Windows. Basically, the conclusion is that Windows is screwed and this won't work. Which is quite funny. But anyway, you see here, run it, it basically prints out garbage. And I can't get it to print out the ASCII codes in UTF-16 format. It's always in UTF-8, which prints ASCII codes. So it does work, it's just that Windows is screwed. Anyway, so it's supposed to work, but the way it works generally is it uses 3 bytes to represent 1 character. That's how it works. So that's why it's a length of 6, even though I only wrote 2 letters. I wrote 2 Chinese characters, it's the length of 6 because there's 3 bytes per character. That's how it works. Anyway, so you can represent ASCII in Zig, but good luck getting it to print on Windows. There is also like any type, but that gets into generics, but we'll get to that later. Alright, so that's the basics of the type system. So I've gone through, I haven't gone through structs yet, so structs, I kind of showed it. So we write const, the struct name, say like, I don't know, user, equals struct. Like so. I'll zoom in a bit. Close this. Make sure there's a semicolon at the end. Let's say, for example, we have, I don't know, name is a const U8. Let's say age is, let's say usize, because it makes sense to make it a usize, because it's unsigned. And let's say, I don't know, occupation. And for the occupation, we're going to make an enum. Say const employment type. I'll say job type, easier to write, equals enum. And let's say, I don't know, doctor, lawyer, I don't know, receptionist, teacher, scientist, whatever, it doesn't really matter. And then we write here, occupation equals job type, like so. Then I'm just going to get rid of a lot of this. So I'm going to get lots of errors by deleting all this, but we're going to get rid of that. And we're going to fix this. And we're going to use it for something else. And I'll fill it in later. So let's create a struct. So we're going to say a user. That's what I call it, right? Yeah, user. So again, I like to write the type next to it and do dot. Again, we got unused local constant. Of course we do. We go user, and let's put in here any. I believe that will just print the type, but we're going to get errors. Expected after type. Oh, sorry, you don't write this here. That's me being weird. We're expecting a comma, really? Sorry, I'm completely writing this wrong. Like that is what I was expecting. And we're missing struct fields. What does this mean? So we don't have default values in this. Because we don't have default values, it's expecting you to fill them out. So say, for example, we make the age default to 0. Then we can not include that here. But if you, let's say, for example, we do this. Unknown. And the job type is job type dot. You can also just use dot lawyer. It will infer what it's a job type, so you don't need to write that. So now we don't need anything and it doesn't give us an error. So we'll use the default values. But if you don't have the default values, if I take this away, then do this, it's now going to expect the default value. So we're going to have name here equals John, like so, and then it will go away. But you can specify. So let's say the age is 25, and let's say he's a doctor, doctor, and then we can print that. And we're printing name equals that and age equals that, which is not the best way to do it. So we probably should specify. So I'm going to go s.name. Let's go age. We don't need to do anything for that. User.age. And then occupation is an enum, so that should print anyway. Occupation. That should work. Remember to put in s because it's a slice. So John 25 doctor. There we go. So if you don't want to have to write this every time, you could also just write a method. So methods go inside structs, which is very useful. So if you write fn like this, let's say print. Say print, make it void, and let's put this into here. But why are we getting an error when we do that? Why are we getting an error? Because it doesn't know what user is. What's user? What's that mean? And there's no inbuilt. So let's say if you're using Java or C#, it will put in like the reference parameter referenced to the actual object. You can't do that in Zig. You have to specify because you could pass by value or you could pass by reference. So what you normally do is you write self. Let's say you can pass it by value, user, if you want. And then you could write here self, like so. And that would work fine. You could also use it pointed and make it const, so you don't want to change it. So we're not, because if you do this, you're copying it. So you're copying a pointer and a length, which is about 128 bits. A pointer size, so it's about 64 bits, and then a i32, I guess, is an enum, so that would be 32 bits. You're copying this data. If you don't want to copy it, you could just do this with const, or if it's actually want it to be mutable, just do this. I'll just make it const, so we're not copying it, and then we can try and print it. So we can just do this, user.print, and we're going to get an error. Why are we going to get an error? It should give us an error if it hasn't. I32, that's an old error. For some reason it's not giving us an error, but it will give us an error when we actually run this. Apparently it won't. What's weird is I thought that has to be public. Apparently it doesn't need to be public, that's weird. Okay, I'm completely wrong. I thought you had to mark this public, but apparently not. I think everything is public in struct anyway, unless it's like a file. That's interesting, I actually learned something there. Anyway, so apparently you don't need to make them public. But we have the self parameter. Say, for example, we want, I don't know, you could also do something like this. Fn print name self, we get a const pointer to user. What you can also do is you don't want to type the name each time. You can go const self equals at this, and then type in this. Sorry, self, what am I talking about? self, make a void, and we can just copy this, get rid of that, and just print the name. And then we can just call here, so if we make a different function for the age and whatever, all these. So what we'll have to do here is we'll have to put in, say print name, and we have to put in the self parameter, which will be put in for us anyway. Print age. Should probably give this another name. And print occupation with a self parameter. And then we can just call print again, and we'll just print. It will probably print with new lines though, because we put new lines with John 25 Doctor. Anyway, so that's how methods, the kind of the basics of methods. So you put them inside the struct, which I always prefer, and use the self. All right, so that's enums, that's structs. I should also go into unions. So unions. So the way unions work is they basically, let's go const union equals union. Let's say, for example, we have, I don't know, big value is an I64. Small value equals I8. Medium value equals I32. And let's create const, I don't know, union example equals, we call it union equals dot medium value. Yeah, it has to be inside a tuple equals, say, 10, like this. And then there's std.debug.print. Let's print debug print. Get me this dot union example. I'm not sure if you. I don't think you need anything for a U because it's just an I32. So right, I worked it out. Okay. Yeah. So yeah, if you want to print out, you don't need any. I think you can just type in here. So you have to type in the actual value depending on what it is. And I believe how unions work is if you have the wrong type set. So if you say small value, it'll give you an error. Yeah. See. The wrong value because the medium, it's kind of like a bool, I believe, or like in, so if you set the value to medium value, you can't use the other values. But how unions basically work is that they will be the exact size of the highest thing. So this is a 64-bit, so the whole memory will be 64-bit. If it's a 32-bit address, it will just use the 32 bits within the 64. So it's the size of the biggest element. And whatever you set will basically be inside it. So we could then set the union to something else. Let's say we make it small value equals 1 and then dot small value. And we don't need to do this. We can set the new value like that. Cannot assign to constant. Okay, make it mutable. See, Zig is very strict. Zig is absolutely very strict. And make sure you specify all intent. So here we go. We got union 1, union 10, union 1. We should probably put a new line here so it doesn't do that. Put a new line here. Union 10, union 1. All right. So those are unions. They're quite useful. What's even more useful is a thing called a tagged union. For a tagged union, we'll take in an enum. So let's create an enum and let's create, let's say const. I don't know, values, I don't know, whatever, equals enum, and we're going to do exactly the same thing here. So big value, small value, medium value, the semicolon. So when you use tagged unions, they have to actually match the names inside the enum, otherwise it won't work. So the advantage of using a tagged union, they're generally better than regular unions, is the fact that you can use switches. So I can show you switches. So I'm going to make these separate types. Let's say const2. The language server has somehow crashed. I don't know why. Doesn't matter. My language server still works, so I don't really care. Union example. And then we got to write the types. So we have obviously big value. I haven't gone through switch yet, but I'll go through it in a bit. We'll go through it now, actually. Why not? It's right here. Dot small value. All right, you got to take the value. Zig uses these kind of weird capture blocks a lot, which does take a lot getting used to. Say print, debug print. It's not going to fill it out for me. Then there are all used. There we go, value 10, value 1, because that's what we've set. Value 10, value 1. Those are unions. You can also put any type you want inside these. So you could put in, here you could put in a user. So the medium value will be, I don't know, user. And this, the big value, let's change the names. So let's say this is now a user. This is a bool. And this is an integer. Bool is a boolean, integer, and user. Because we don't, that doesn't exist now, so we're going to make this integer equals 10. And we're going to make this bool equals false. Big value doesn't exist, of course, so we're going to write bool. Errors go away, okay. See here, value 10, value false. So there's the tagged unions. They're quite useful because you can put any type in them. We can also make another union and make it a union example 3. Let's type it and make it a user. And then we can actually link to the user we created, user. So now we're, okay, unused local constant because we're not using it. Of course, Zig is going to complain every 5 seconds. We're going to write this through here, save it, and then that will print out the user. Like name, da, da, da. But obviously we didn't print out the name, so what we can do is we can use the print function we made. So we can go value.print. I believe that will work. Because value is a user, it's going to call the print function, and we call the print function. There we go. All right, so those are unions, tagged unions, enums, structs. I hope that makes sense. All right, now let's get into control flow. So control flow, I'm just going to delete most of this. So control flow is actually very simple. So if you're familiar with C or any language similar to that, like Go or anything like this, Python, whatever, it's very similar. So if is exactly the same. So we go if in brackets like that. Let's say we create a bool condition bool equals false. Let's say if condition. So you can do if condition. I prefer not to do that. You can also do the negation if you want. I prefer to do false or true. It's just easier. It's better for me because it's more specific, easier to read. But you can do whatever you want. And then we can also use an else like this. And we can go debug print. Server's not working, doesn't matter. You say condition is true. Copy and paste that condition. Then we're going to mutate this. Condition equals false. Print condition. Condition. So this will say condition is true, condition is false, without a new line, because I should probably put a new line. You want to remember to put a new line. You can also make a helper function if you want, debug new line. Condition is true, condition is false. There we go. So that's if statements. You can also use else if. So else if. It's kind of redundant in this situation because it's either or, but you can use else if and then you can use else, which obviously should be impossible in this situation. So we can just type in else, we can use else and make it impossible. So if condition is true, condition is false, or it's impossible. You can also use returns if you want, so you don't even need to use else. You could just write return here, and then you can put if here, like that, and then return, and then say impossible. So you don't need to use else if you don't want. Return with a semicolon, and this will do exactly the same thing, just without the else. It's exactly the same control flow. So just quickly, because I forgot to mention it, if you want to do multiple checks in one if statement, then you use and, or you use or. And will be both, or will be either. You can't use and, the bitwise symbols, or you can't use or. Those are invalid. Alright, then I've done switches before. So switches are a bit strict though. So switches, it's not auto doing it, doesn't matter. Condition. Say true. Again, is true. I'll just do this. This will write it twice. So say is true. There we go. So the reason, well, so switches basically, if I make this an integer, for example, if I go const integer i32 equals 1, and let's make this now integer, and let's make this 0 and make this 1. I'll say is 0 is 1. We're going to get an error when we do this. It will show here. Error. Switch must handle all possibilities. So Zig wants you to be strict. It is strict. So what about edge cases? You know, integer could be, you know, thousands of values. So we have to do the other values. The simplest way to do that is just to use else. You can use unreachable if you want. Unreachable, like this. What unreachable will do is it will basically panic. So if you'll make this 2, it will panic. I'll show you a panic. It'll say panic. It'll say I reached unreachable code. Panic. That's what panic does. It just crashes. But you can do anything you want. You say unexpected value. Integer. Gotta remember to write a new line. Always forget to do that. There we go, is 1, alright. So the else just covers all possibilities. There are other things you can do as well. You can do stuff like this. So you can do 2.10. And then I'll copy and paste this. And say between 2 and 10. I'm not sure if that's inclusive actually. Let's have a look. Make it 10. Will that work? Is it inclusive? Dot dot. Do you use dot dot dot? I think you do that. Yeah, triple dot. And between 2 and 10. So it's inclusive. So it's 2 to 10. You can also use commas if you want. So you can do multiple values like this. Comma 2, 3, 4, 5, 6, or whatever. Like that. Obviously it's redundant at this point. But you can make it very useful. Say for example you have some kind of like we're going to call this char and make it a U8. Let's say we make it A. And then we want to make a function is letter. So fn is letter. We're going to type in char U8. Input, we're going to return a bool. And we're going to go switch on the char. And then we're going to do something like this. So we're going to go between a dot 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 and z, which is not a z. Return true. Between a dot 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 and z, return true. Else return false. So const is letter. bool equals isLetter char. And it's going to complain at me because I'm not printing these, I'm not using them. So we're going to do this, that. We say char isLetter. So to print a char, we write C. Otherwise, it's going to print the number. I'll show you both. And then say bool, you don't need to write anything, so isLetter. Right, so I'm printing quite a lot here, but it doesn't matter. So at the bottom we have char value is A, int value is 65, and isLetter is true. So this is kind of the usefulness of switches. You can do betweens like this, which is very useful for isLetter, because if you had to write like A, B, C, D, it's, you know, tedious. Anyway, so that's switches. If you use an enum, for example, I did make an enum before. If you cover all situations, it won't need the else block. But if there are situations where it's unhandled, you need to use the else block because it wants to cover all edge cases. All right, so yeah, those are switches. That's if statements, switches. Then we have for loops. So for loops are a bit weird. So I'm going to make an array. I'm just going to delete all this. I'm going to make an array. Let's go array. Of course, unused local variable. It's going to complain at us. Doesn't really matter though. So what we need to do here, so we want to use a for loop, right? So there are multiple ways of doing a for loop. They're a bit weird. Say if you're used to C, you can't do something like this. Int I equals 0, I less than array dot len, I++. You can't do this, unfortunately. It'd be cool if you could do that. Well, it's actually easier. It's actually easier in Zig. What you do, so take away that, put a dot dot here, put that here, and then you make these capture brackets, like and you put I. And then we're going to make a value, i32 equals array by I, and then we go debug print is the value. Like so. This shouldn't give us an error. We're fine, and we can print. So it prints the value 1, 2, 3, 4, 5. Okay, like this. If you don't want to use the value, you just want to write something. It's a bit weird though. Say you could do something like this. You could go 5. You just want to print the 5th value, which will be an error because there's not 5 values. We're going to use underscore because it's going to be, you're not using unused variable. So underscore will get rid of that. So we just want to do the same thing 4 times. It's going to print out 4 or 5. It's going to print out 5 times. That's a simple for loop. Also, we have while loops, so we could also do this. While. So we could say var index usize, and we're making it a usize specifically for one reason. I could show you here. I is actually a usize. I can show you that pretty simply by doing this. Var value i32 equals undefined. I'm just going to get rid of the array because I'm not going to use it. And then here, we're going to set the value equals I. And then we're going to go debug print I equals this, new line, value. Sorry, value should be that. Say while index less than 10. This actually works in Zig. See, it doesn't work here. It found usize, so we have to cast it, which I'll go through casting a bit later. But it's a usize. This is how you kind of find out it's a usize. So I specified it's a usize and not, you know. But yeah, we are actually using array, but it doesn't matter. Okay, I'll get rid of this. I'll keep that actually. I'll get into optionals later, but for now I'm going to do this. So say if index higher than equal to array.len, and we return null. But optional is basically a union that has a value or not. Return array by index. No. I'll go through optionals in a bit. Index. I'll say value Okay, so this is going to do exactly the same thing, but it's going to break because we're going too far. 1, 2, 3, or 5. This is exactly the same thing. Because we have safe array access, which we're using a slice, because it's the simplest way to do it, because we don't have to specify the length then. So we put in this safe array, but we don't need to necessarily do this. The way nullibles work, I mean, I'll do it in a bit. The next thing I'll do is optionals. But we're basically saying, it does it have a value or not? If it doesn't have a value, break, because it's obviously outside the array index of the array, outside the bounds of the array. All right, so that's while loops and for loops. What you also can do is you can use an iterator for loop. So you can go for array value debug print value new line. This will do exactly the same thing as what I'm doing below, but it will make an iterator for you. So it's going to say 1, 2, 3, 5, 1, 2, 3, 5. Yeah, see. So this does exactly the same thing. It's kind of the lazy way because it means you don't have to create a temp variable. It's also safer because it does the length for you in certain ways. I generally prefer to do it with the for loop way because you're using the length anyway and you have more control. And you can also print I, because if you do it say you'd have to do it like this, you could do I if you want the I as well. Anyway, there is also another thing you can do. You can take away this. Yeah, so alternative to doing that is this colon. So you put a colon, then you put this. So this will basically, on the continue expression, then you don't need this. So this does exactly the same thing. It's going to write exactly the same thing again. It's going to write 1, 2, 3, 5, 1, 2, 3, 5. Yeah, it's going to write exactly the same thing. So that's an alternative. It basically runs on every continue. And it's almost exactly the same as a while loop, really, to be honest. There's a multiple way to doing it. Those are the ones I use. I normally just use regular for loops. Anyway, that's basic control flow in Zig. Okay, let's go to errors now. So errors are one of the most important things in Zig because it's kind of... it's probably one of the biggest selling points of Zig is the error system. So I'll show you the very bad way of why errors are so good in Zig. So say, for example, we create an enum. Let's say HTTP error, HTTP status. All right, so I'll show you what I just made. Okay, so open pages. We have a list of pages. We're gonna mistype this, and we have the valid pages up here, and then we have slices of the same, just to compare two different slices, because there's no actual inbuilt function to do that. Well, there is, but simpler just to make my own. Anyway, so yeah, we look at this here. The slices are the same. We say okay if it is, otherwise we say not found. And then we have to put the status here. Well, say for example we find a bad status. Let's say if with the new line, you always got to write a new line. So we have opening this, not found. Status not found with a BBK. All right. So that's basically the thing is with this is you basically need to you need to either return it or you need to pass it as like a reference, because say if you want to have another return value, you have to pass the HTTP status as a pointer. Say something like this. So you'd pass status as a pointer to HTTP status. Maybe this void, or maybe you make this the page. I don't know. Say you make this the page, and then make it maybe nullable. I'll go through nullables in a bit. So, say for example, we write, I don't know, page here, whatever. Otherwise, we write null. And then we've got to set the value. So we go pointer to status. Status. The dereferencing syntax is kind of weird. I'll show you also the optional syntax after this, which is even weirder. So that works. So status not found. The thing is, we have to pass it by reference. We have to check with an if after every situation. It just reminds me of Go. So I'll show you the idiomatic Zig way of doing this. So instead of error, well, instead of an enum, we're going to make this an error. We do this, okay? We can't have values on the error, I'm pretty sure. And then what we're going to do is we can't make this a status, so we're just going to get rid of this entirely. And then we're going to get rid of this entirely. Just get rid of it entirely. And then we're going to make this return an error. So instead of making this optional, we're going to make this return an error. Get rid of the optional. We can get rid of the status as well. Here. Return the page. Page here. And here we're going to return HTTP status. And we don't need the OK. I'm going to call this HTTP error instead. So we're going to type HTTP error not found, like this. And say if we want to use that error, so if there's an error, we type in catch, and we use one of these weird blocks again, error, and say debug.print, debug print. We don't even need to write anything here, we just do this, new line, error, and then return. And it doesn't have a semicolon, and we're using status, which you don't need anymore. So we get rid of that. So we don't need a status, we don't need that. It's basically just, it's an error union is what it is. So we have the exclamation point next to it, which basically means this could return an error. So it's either an error, what it is basically it's a union of an error type, one of these enums, or a whatever the value is. So in this situation it's a const u8 slice. So it's either page here with whatever the contents are, or not found. And if it's an error, we use catch, which will basically do whatever we want. We could also just return. So I'll show you the 3 ways after this, but I'll just show you this working. This will do exactly the same thing. Let's do exactly the same thing, I'm pretty sure. See here, error.not found. There we go. It is exactly the same thing. It's just more streamlined. You can also just use try. What you can do is the laziest way possible. So you catch error here. And copy and paste this. That here. And then we're going to make this one return an error void. And then we're just going to use try. Try. And we're going to get rid of the catch. Like so. What try does, if this is an error. So basically, if this is not the value and it's actually one of these error values, return it. That's all it does. So it basically, it's the equivalent of writing if whatever equals error, return error. Whatever, something like this. That's basically what it does. Try does that alone. And you just write try and it's easy. You can also, if you want, get rid of this entirely and just write try here. And then use try, make that an error, and then use try, and then you don't even write this. You just try that. Depends what you want to do. So this will just basically error. Say error, not found. And I will show you where. Because when you return an error from the main function, it will basically panic and show you what happened. Return error not found. Error not found, and then show it. So you don't even need to ever print it. You could just spam try if you want and go all the way down to this function. The more thorough way, say if you want to do something else after this. Say if you want to continue, do something else. I don't know, something else, dot. Then obviously we can't return that. So again, catch, error, do this. Get rid of try. You can't have both try and that. Because try will basically return. So this will error and then do something else. I'm just going to put a new tab here so it'll be more readable. So that's the simplicity of error messages. I mean, you just use try most of the time. You can also use catch. What you can do also is catch can give a default value. So I'll just quickly make something where, say, I don't know, let's say fn divide. Say we do something like this. So we go const divide result. Divide result I32 equals divide, let's say 10 divided by 0, and we're going to catch 0. And we're going to debug print that. Divide truncate. Okay, this is Zig's being annoying here then. Must use div truncate. Like this. That's just weird. Zig's being very, very pedantic here. Anyway, I'm just trying to show a simple example, and of course Zig gets in the way. Anyway, divide result 0. I should put a space here so you can actually read it. So what does this mean? Basically, it sets the default value. So if this is an error, we found an error here. It's divided by 0 because we're setting 0. So we put the value as 0. It sets a default value. Or you can catch the error like this and print it. And so if it's an error, we're just going to return. This will be error divided by 0, like that. The alternative is to use if, but if is probably the worst case scenario. You really don't want to use if most of the time. So you can't actually infer the type if you use this. So let's do this. If divide result, in brackets, res, else. And we're going to capture the error like this. Okay, no errors. So error divided by 0. So here, for example, it says if this is an error, capture that in this temp variable and then use it. Else it is an error, use this temp variable, print it. But the problem is doing this is very, very long and tedious. It also means you have to use an if, and then the bad situation is after, which creates nesting. So the best way to do it is just to use try. Just try, get rid of this, try, and then print the value. Let's copy this. Use try, print the value. Doesn't know what res is. Divide result. So this will say error, return, divide by 0. That's the simplest way to do it anyway. Try is basically the simple way to do it. Okay, let's get to optionals. So optionals are similar to this, but instead of the exclamation point, you use optional. Optional, and you can do this. Instead of this, we're going to return null. And then you can say optional I32. And if you say if divide result equals null, then I'm going to say something like debug print divide by 0. This is an optional, so we have to do this to make sure we specify it's an optional. The other way is to do if again. Of course, you can use if. I forgot I was using optional, so yeah, divide by 0. So basically, this returned a null, which I basically would just be a union of a bool with the value or not, and then the actual value. I'm not sure exactly how it works internally, but it's some kind of union. That's an optional. You can also have an optional pointer. So with this question mark thing, you can also use if you want, which kind of defeats the whole point, because you could do this. If divide result, like this, result. It's exactly the same as before. If optional, if it has a value, put it in this and print it. Return, really. Get rid of the return. Okay. What does it say? Divide by 0, value is null. Put a tab here. So that's the alternative. You can also just unwrap it if you want, but this is dangerous. If you just say, if you don't check it, and do something like this. Let's say you go divide result dot optional, and say I don't care. I don't care. It's going to give you a panic. Say panic. Attempt to use a null value. But basically, Zig, when it's in safe mode, if it's in debug mode or it's in release safe, it will check and say, is this value actually there? And if you try to use it and it isn't there, it will panic. But you should check, obviously, the easiest way to do it. So there is another keyword you could use. You could use or else. Or else, which I can't spell. Or else 0, like this. What or else means is basically if it's null. So it's a bit like try or catch. Divide result 0. So basically, do this if the result is 0 or result is null. set it to 0 as a default value. You can also do whatever you want here. You could say like return. You could just return, and it will just end. If it's null, return does nothing. There we go. But probably best not to do that. So or else, or else is for null, or we can also use if. So I'll just summarize this. So optionals syntax, you go this, the type. So you'd say like i32, optional i32, or you could go optional const u8 slice, something like this. Check nulls. So yeah, return null, obviously, return null. You can check nulls by doing, you can say, for example, if value equals null, return, something like this. Or you can do if val, that creates a capture block, else, like so. This is null, not null, use the value. Alright, and then there's dereferencing it, like getting the value straight away. So you go value dot dangerous if not checked, panics if null. So that's optionals. So optionals are very useful with pointers, especially. I'll just show you pointers quickly. So say, for example, we have, I don't know. I'm just going to clear everything just to make it clean as possible. Let's say we have get pointer. We're going to make this an optional pointer to an i32. And we're going to put in, I don't know, slice. Say slice of i32. And the index will be usize. So we're going to get a pointer to an array. Array equals i32u 1 2 3 4 5. All right. So let's say we want to get pointer. Get pointer. We're going to say const pointer equals an optional pointer to an i32 equals get pointer, which is going to be an array with the slice 0 dot dot. I think you use that. Then we go 1. Let's go 5. Let's go outside the bounds of the array. Like this. And then we have an optional pointer that will be null in this situation, because we're going to check it. We're going to go if index higher than equal to slice.len, then we're going to return null. So we have a null pointer. Null pointers are a lot safer than they are in C. Otherwise, we're going to return slice by index. And we're going to return at slice by index, so it's a pointer. And then we're going to say if pointer equals null. We could panic with the std.debug.panic. I'm not sure if panic takes in, let me go look. Panic. Pointer is null. Otherwise, we're going to use the value. Let's go debug print. Pointer. Here's where we get the weird syntax. So for pointers, you want to dereference them, which means you need the pointer syntax. But this is an optional, so we need to use the optional dot question mark dot pointer, which is where it gets kind of weird, because you can also infinitely do this. Infinitely go pointer to optional to pointer value equals this dot referenced. Okay, that should work, I think. Getting an error. Do we have to use should this be just make it constant, it's fine. Doesn't like that. Found optional. Now this should be a const then. It's very strict. Okay, found expected type, found... For God's sake, man. Zig is so strict. Okay, are you happy now? We've made this const anyway, so because it's a pointer, we've got to make sure this is const, this is const, this is const, this is const, because we could be checking that. Which, I mean, Zig does a lot of checking, which is obviously it doesn't want to change mutability, is why it's doing this. Anyway, so we run this now, and it should panic. Yeah, panic pointer is null. So @panic is very useful. There are lots of built-ins in Zig, which I might show at the end. So @panic will basically just pointer is null. Ugh. So it's a lot safer because obviously. We won't get a seg fault. If we just do this, let's say we comment this out, it's a lot safer because it won't give you a seg fault. It will say, attempt to use null value. It's just a lot safer because it checks. When you're in release safe or debug, it actually checks that the pointer isn't null. So it's not like just seg fault and end. It actually shows you where, what happened, why. So it's a lot safer. Anyway, so let's say we make it 2. And then we'll have a pointer to 3. 3 should be the what we print out. There we go, value 3. There we go. So now we've got a pointer. We can also make it mutable. We can var, and then make this non-var. And then you've got to make this non-const. And then we can change the value. Pointer dot u plus equals 1. And then we can also, this will actually print out the array. So we get a debug print, say array any dot array. So this should change the value of the array because it is a mutable pointer now. See here. So we've changed the second index to 4 because it is a pointer. That's how pointers work. Making it optional. You can also just do this if you want. Say if you don't want to deal with the optional after this, you could say, for example, let's call this optional pointer, and we can go const pointer i32 equals optional pointer dot question mark. And then we don't have to deal with the dereferencing, and we can get rid of this. And we can get rid of this. And it does exactly the same thing. It will say exactly the same thing. So yeah. All right. So those are optionals. Then we have errors. So errors are an enum type, but unique. Question mark returns an error. You can actually specify the error if you want. So what you can do is say in this we have HTTP error and we're returning that. Let's say open page. I'm going to return HTTP. So let's specify HTTP error. So now it's either an HTTP error or it's a constituted slice. So you can specify if you want. Normally it's inferred. There are some situations where, say if you use recursion in Zig, the compiler can't work out what the type is, so you have to actually specify, but most of the time you don't need to, and you can actually put whatever you want there. So you can use multiple error types. But it's normally inferred, so you don't actually need to specify. So you can specify. So error value or i32. HTTP error or i32 equals HTTP error value or i32 infers error type. So we have if, let's say value val, which it would be like if not error, use the value. Else, you don't actually need to capture the value, but it's just best to do it. If error, use the value, use the error and print it. That's the worst case scenario though. The simplest way is just use try. So you use try function, which is if error, return it. And you need to make the function you're in return an error as well. So you're basically passing it down the line. Or you can use catch. So you get function this catch 0, which sets the default value to 0 if error. Or you can do function catch unreachable. Catch unreachable just panics, basically. It just panics if error. Or you can go function catch error in the capture blocks, do this, and then do something with the error. So if error, use the value, and you can print it and return it, and do whatever you want. Those are basically errors. They're a lot more streamlined. I try to recreate Zig errors in other languages, and it's very clunky. I can show you what it looks like in my C# code, for example. So here I create a pass result, which is just an enum with all the error types, with all the error things, and I have to check if pass result not equals OK, then you print it and then return null, or if format result not OK, print it, return null. You basically got to set this every time, and you got to pass it by reference every time. Whereas Zig just does it. It's just so much more, because basically you catch error and then print it. You don't even need to create the variable, or you could just use try and it returns. So if you just want if error return, just instead of putting anything here, you'd literally just delete this, put try, take this out of there, delete this. And it's done. Like Zig is just so much better because it's built into it. And it's also very streamlined as well, because the Rust way would be to basically spam result, because results and error unions are very similar. They're both tagged unions, but in Zig it's more streamlined because you don't just specify the error type. So Rust would look like this. I don't know. Maybe that's even a null type. I don't know. And basically everything looks like this. It just like the result this, result that, result this, result that, and just pollutes all your function signatures. Whereas in Zig, you literally just write exclamation point. That's it. So instead of result spam, this will just be error void. Get rid of that. Error void, done. Instead of this result, you don't even need to do that. Just put in result string. Just error. That's it. It's just a lot more simple than Rust is. It's a lot more streamlined, which is why I just prefer Zig Errors. Zig Errors are just the best. They really are. Probably my favorite error handling method in all of programming, to be honest, because it's the most streamlined, the most simple, easiest to use. All right. One thing though, if you don't actually, so what I normally do is I never infer the type, because if you infer the type like this. Let's say make it an error instead. So yeah, we go back to the divide thing. Here, if we just infer the type, this will actually be a really, really complicated type. I'm just going to restart VSCode quickly. Yeah, so it's an optional to my32, which you can't actually specify. Anyway, if you do this and you forget to actually return the error, this is actually going to be an error union, and we're going to try to print an error union. It's going to cause issues. So maybe you type any. The thing is, this is an error union. It's not an I32 anymore, because if you don't write the type, it will just whatever you wrote here, and this will be an error union. And how do you do an error union? Like, how do you deal with that? How do you print it? You got to write any. It's a problem. So basically, I specify I32, and then we get an error saying you didn't handle the error. This is not an I32. This is an error union. So you need to catch the error. You need to use try or catch or something to catch the error, which is why I don't like inferred types, because it can lead to this kind of foot gun situation. But now it says 1, it's fine. Anyway, so those are errors. All right, let's go through a few other debugging methods. So there was obviously @panic, which I showed you. I'm not sure if there's a std debug.panic. There is, yeah, there is. So you can panic with actual arguments if you want. You can also catch and switch if you want, which I rarely use, because most of the time I just want to print the error and don't really care. But you can switch on the error if you want, depending on what the error is. But I generally don't bother doing that. But you can actually also just leave it. unused local constant. Let's just print the result afterwards. So it shuts up. So now we're going to get an error. Say unhandled. And I say it actually tells you all the unhandled situations, which is actually very useful in Zig. So say if you don't know all the error types, you type error.divide by 0 and it tells you what errors haven't been handled because it's a switch. I generally don't like to use this because I don't need to half the time. All I need to do is just print the error. So debug print. You can use panic. Yeah, I was going to show panic. So you go std.debug.panic. And what this does is instead of the other panic, you can actually put values in it. So you can say instead of this, I'll just copy and paste this into it. Because the B is the thing that caused the error, we can actually specify what the B was when we panicked. So panic, B is 0. Instead of just using @panic, what @panic does is doesn't allow you to put any values in, it's just one message. So you'd say like, I don't know, error, something, divide by 0. Error happened, I don't know. You don't even know, you can't use the value as the problem. Let's get rid of this. It's unreachable code, we can get rid of this, and we can get rid of the error then. Oh, catch unreachable. You don't even need to do this, you can do this if you want. Get rid of that. We don't even know what the error because panic doesn't allow you to put arguments in. You can't do this is the problem. Anyway, so panic is better if you want to print like values. You can also assert. So you could do something like this. You could std.debug.assert, which assert is probably the simplest function you'll ever see in your life. It literally just says if not okay, unreachable, which just means panic. Panic if if it fails. So we're going to say b not equals 0, and this will panic. A panic, assertion failure, unreachable code, not equals OK, and it comes back, assert b not equals 0. That tells you where. So you can use asserts everywhere if you want, but it does panic the program, so be careful doing that. Alright, now let's go on to allocations. So if you'd like more information about this, I do have a video, stack versus heap. But basically in some situations, you need to ask the operating system for more memory, and you have to manually do it. In Zig, it's all manual. In like high-level languages, it manages it for you. So say if you create like a string, it will be on the heap, and then garbage collection will remove it for you. And it does this for certain reasons. Generally, you want to allocate memory when, number one, you don't know how big the size is. So if it's a runtime known value, you need to use the heap value. Also, if it's like, for example, you go into a function and you return out of it. I can show you an example. So say we go fn get pointer, right? And we're going to return a pointer to an i32. And then we're going to do loads of other stuff. So it should be 10 in theory. We're going to const number equals get pointer. So we're just going to go to 10, do something for a bit. Maybe create an array or whatever. We're going to create an array. Okay, we didn't have a new line. It actually didn't go past the stack value. It didn't actually have what I thought would happen didn't actually happen. It stayed at 10, but basically this you shouldn't do this. All right, so I was trying to show you what happens when you actually have an invalid dangling pointer, but it wasn't cooperating. All right, so it wasn't cooperating. Anyway, so basically when you return here, this is a stack pointer, a stack variable, and then we return a pointer to it, which is invalid, undefined behavior, which basically could be overwritten by certain things. For some reason, I can't get it to work. I don't know why. It doesn't matter. Anyway, so in most situations, you shouldn't do this. So the way to do this is to allocate, because it has to persist. It has to exist outside of this. So the way we do that is through allocations. And there are multiple allocators in Zig. I'm going to show you using my tutorial project what allocators exist. Doing that. All right, so allocation syntax. So it depends on the allocator. But we have the page allocator, fixable, do we have different allocators here? Here we go. We've got different allocators. So we have the C allocator, which is normally used when you're linking C code and C libraries, and it uses basically the allocator from C, and you have to use libc when you run it. So you run zig run whatever the name is and .lc, so libc, so you're linking libc. It doesn't do that by default, Zig. Then you have the page allocator, which basically will make a syscall asking the operating system for more memory each time, so it's probably the slowest. But it's also the most reliable to get memory and, you know, remove the risk of running out of memory. The fixed buffer allocator, so sometimes you have a function that requires an allocator, but the fixed buffer allocator will basically use stack memory, and you put the stack memory, you put a buffer into it, and it uses stack memory. So you don't necessarily need to have heap. You could use stack if you want, and still have like things you need to allocate for. But know that this, you know, if it goes outside the range of the buffer, then it will cause an error. So you need to be careful and make sure you actually have a big enough buffer. The arena allocator is, you basically put another allocator inside the arena allocator, and then you can free it all at once. So it's basically like, imagine you allocate, I don't know, loads of like loads of dynamic array lists, or like dynamic arrays that can grow in size. You allocate a load of these, and then you don't really want to go into each one, for loop, free them all individually. So it basically just does it for you. So you use the arena allocator in that situation. And the best example I have is actually my compiler series. I'll show that quickly. So in my compiler series here, we get the const page allocator, which is the allocator that uses a syscall every time. And then we get the arena allocator from, I believe it's in here. Arena allocator is sdu.heap.arena allocator. And then allocator itself is se.mem allocator. And then we have this defer keyword. And the defer keyword works exactly the same as it does in like Odin or Go. It basically will do something at the end of scope. So wherever you next find like your return or this close curly brace, it will run whatever's here. So this, the standard idiomatic way in Zig is whenever you allocate or create something, you d'init right after with defer so that you never forget. Because it's also, it means that if you have like, say, 10 early returns, you don't have to put, you know, arena.dinit on every one. It does it for you. So it's a very, very big quality of life improvement. Defer. There's also air defer, which basically means when it returns an error, do this. So you can do that as well. And this basically will, so everything I allocate in this entire project will just go. I don't need to free it all. It just does it here now for me. So that's the benefits of arena allocators. We have the debug allocator, which before used to be called the general purpose allocator, but was renamed, I think in update 15 or 14, don't remember which one. And this is basically for safety. It will detect memory leaks. I also have my own that I made recently, which is a tracking allocator. I made one a tracking allocator a long time before earlier, but it wasn't actually a full allocator. I'll show you this now. So yeah, I'll show you the tracking allocator later. It basically allows you to see if you've got memory leaks, or it just basically tell you how many bytes you've allocated, how many frees, how many count, how many allocation counts, how many free counts. It does it for you. Anyway, so that's my own. But you choose the allocator you put in as well, so it works with any other. So those are the general allocators, and most of them are in heap. So I'll show you how to get them. Let me go back to where I was. So back into main.zig. Let's fix this, shall we? So what we generally do to fix this is we put in an allocator, and this is an allocator, which I like to, so I don't like to like sed.mem, so I just put const allocator as an alias. Const allocator equals sed.mem dot allocator, not alignment, allocator. And we're not using the allocator because Zig's annoying, so we need to here call allocator. This is now going to be a pointer. It has to be a pointer. Dot create, and we need the type i32. So we're creating an i32 on the heap, and then we're going to return this like so. And we're going to get an error for some reason because it's not const or what. We didn't put an allocator in. So we need to get the allocator. So let's just use the page allocator just because it's the simplest to use. We're going to get rid of all this rubbish first of all. So let's get the page allocator. This is an allocator equals std.heap.all. What's it called? Page allocator. There we go. Right, I'm completely wrong. A page allocator is like this. There we go. That's the page allocator. We do need here to. So we have. Let me get rid of this. Found out of memory I32. Yeah, so this actually returns an error. It's very useful that the compiler tells me all this stuff because I normally have to actually run the compiler. So we have to return an error. So either we can return the error or we can handle the error here. But I'm going to return the error, or we can make it null, technically. So we could make it nullable, or we could have the error. So let's just have the error. And the standard error that returns is what's called a, so we can just call try. Try would be the simplest way to fix that. And that doesn't, for some reason, why is that? Ah, right, sorry. I'm derping a bit. So it is a pointer itself. You're not supposed to reference a pointer, because if you at the pointer, you at, yeah, anyway. It is a pointer itself, I forgot. Right, so now we can actually make this const, I believe. No, we can't make it, we should make it const, that's stupid. Let's set the value. So we need to set the value, so pointer, let's say 10. So this now needs to be var. Or does it? No, it doesn't, it can be const. Again, the const means you set it to another, looking to another variable address. Okay, then we have get pointer page allocator. I think this is fine. We're looking for a okay, found that we need to use try or catch or something. So let's just use catch. Unreachable maybe. That's the lazy way to do it. But I said what we're probably just going to do is I'm just going to use try. That's probably the simplest way. Let's use try. Then we need to free the memory because this is a should be a const. Maybe it should be const. I don't know. Let's not make it const. That's no errors. Okay. Then we need to use defer. Page allocator. I'm so confused. Page allocator dot free, and the memory is number, like this. And the thing about defer is if it returns an error, you basically can't do it. So if something returns an error, it's very awkward because say if it returns an error and you use try, it will give you an error. So you're not allowed to use try inside defer expression. So you have to kind of either handle the error or do something. But that should work now. Even though it was actually working before. We're getting an error, are we? Slice of vector I32. Now it's a pointer. So that's basically the correct way to do it. So if you return a value, there's a pointer from a variable. Because if you just return, say, just a regular I32, it will return the value. But in this situation, we're returning a reference to something. And then the reference could go out of scope. So that's what happened here. And the reason, yeah, I just mixed them up because so there are basically four functions you really need to care about. I mean, there's another one, but so there's create, which is this one, which creates one thing, and you put the type in, and it's generic. So we can look at create if we want. Go to create. So create takes in a Comptime t type, which basically means it's generic and depends on at compile. It'll be worked out at compile time. So we put the type in here, we put in I32, we have to specify the type. Then we have alloc, which basically creates a slice, which is again a pointer and the length, and you have to specify the size, which I'll show after this. Then we have, so with create you get destroy, which means destroy is one thing, freeze one thing. And then with alloc, you get free, which frees the slice. And the reason I was getting error before because I mixed them up. Because I rarely actually just declare one thing, but anyway, I normally declare slices or whatever, because normally you use strings or anything like that. All right. Probably the better way to show the dangling pointer problem would be with a U8. We don't need a pointer now because it's a U8. So now we go, let's say alloc. It's going to be a U8. And we do need the size now because if you look here, alloc, it takes in a Comptime t size or n u size. We need a size. Let's say we're going to make it 50. Right? And then we're going to make this now a U8. And we're going to create, say, this is called message. say buffer, I don't know, message or whatever. Then we need to set these values because we've, so what we can do, 18, S, T, hooray, I know the alphabet. All right, then we are going to change this because we're obviously getting the wrong type. We need to make this a U8, and then we're going to print the buffer or message, I don't know, message. Message now needs to be free because it's a slice. Try is fine. We need to call this message dot pointer. You see it's a slice. You see pointer length. Then we have message dot. Let's do this and then slice S. Okay, that's the memory address of U8, right? And then we have these garbage characters. So that basically is on the heap, so it's fine. Obviously, we get a double free if we, like say for example, we do something like this. Let's take away defer and do this. This will give us probably a seg fault. There we go, seg fault. Segmentation fault. What does that mean? Basically means we have a use after free. So we've basically allocated it, we've freed it, and then we're accessing the memory. We don't, basically the operating system doesn't give us permission to access the memory once we've given it back to the operating system. You have to basically have permission to access every memory address. So we put defer here to make sure it happens when we're done, when we're not, accessing it. All right, so this is the basic idea of allocating. You don't want to do this. You don't want to have like stack memory and then return a pointer to it, because the stack memory goes out of scope as soon as you do this. Sometimes it'll be the same, sometimes not. It depends on the situation. I can't get it to actually show you in this. But anyway. So this is the general idea of allocating. So in what situations do you need to allocate? So it's stuff like when you return from a function, a pointer to something, that has to exist outside the function. Or maybe you have a lot of data. So the stack size is about 1 megabyte. On Windows, it's 1 megabyte. On like Linux, I think it's like 10 megabyte, something like this. But say, for example, if you want to open a file that's more than 1 megabyte, you need to allocate because it will call a stack overflow. When you go outside the stack, it's a segmentation fault, stack overflow, really. So if you go over that, segmentation fault, stack overflow. So you need to basically allocate memory when it's too big. But normally you do it when you don't know the size, or maybe you have a runtime value. So you, like, I don't know, getting user input, something like this. That's generally when you want to do that. Or maybe you have a growable array and you don't know how big the array is going to be, and maybe the user can decide how big the array is going to be. You need to allocate in that situation because it's not stack known. In theory, you could allocate a buffer. Anyway, I'm getting ahead of myself. But generally, you need to allocate in some situations. So I'll show you a good example, which is in my compiler series. So the reason why we have to allocate is we have here an array list. An array list uses an allocator by default because it's basically, we don't know how big it's going to be. We don't know how many code tokens there are. Because this is a programming language, there could be 10,000 tokens, and they all could have a long length. That means that's going to be more than the stack size can hold, so we need to allocate on the heap. We're in an array list here, and I'll show you when I actually allocate, if I can. If you look here, we basically pass the allocator to every function. So Zig will not presume that you have a heap, because you could be on like maybe you're on the Mars rover. I don't know, you don't have much memory, you don't have a heap. So it doesn't presume you have a heap, and you have to pass an allocator to every function. And the allocator could be backed by stack memory, it could be backed by heap memory. I'll show you the point where I actually allocate. So here we go. Here I create a text builder, which is a std array list of a U8. So we're just building it based on the size of the string because I don't know the size. It's not known at the compile time, and I only want until like it actually gets to the end of it. So we basically allocate it, and then we convert it to an own slice, and then we return the token. So to own slice basically means it exists, and this puts it in the token, so it's fine. But it's on the heap, so it's fine. Because if I didn't put this on the heap, it would be a dangling pointer. And if you did this for like 1,000 tokens, you'd have loads of dangling pointers, and it would be nonsense. It'd be absolute nonsense if you did that. So we init capacity here, and then we append here. Use it always with the allocator. We're always using the allocator. I'm not sure if you're supposed to do this, but I use pointer to the allocator. But you don't necessarily need to do that. You could just make it. I just prefer to do that, and then I have to dereference the pointer every time I call it. And I've got to use try because it can fail. So yeah, we basically just append and then we to own slice, which will mean you own it, and then we put it inside the token, and that's basically allocating the memory because we need to in this situation because it will go into a Stack Overflow if we have too many tokens. So that's a good example of when you'd need to do it. So array lists. So a good example is array lists. So I can show you some array lists. So say for example, I don't know. Let's say, all right. So this does use the. This is opening a file. This does use the new interface for reading files, which means I don't really understand most of this code because it's completely changed to how it used to be. And it's quite complicated now. Honestly, it's not the best. The simplest thing to open a file now. So this is actually similar to how it was before. I mean, it's a long chain of functions. There was CWD, which means the working directory. You get the current working directory, and then you open a file with the file name, and then read only. So we're not going to write to the file with this mode. Then we have this. We get a buffer of 2. I have no idea why we get a buffer of 2, and then we get the reader, and then use the reader with the buffer. But the reader's only 2. I don't really understand why we're only getting a buffer of 2. That doesn't make sense to me. Anyway, then line IO buffer allocate. Then we're gonna main loop to read data segment. I'll put a link to where I actually got this code from, probably in this description. Let's see what this does. First of all, because it might error. Yeah, we've got an error. File not found. Obviously, it doesn't exist. So we need to actually create the file, and then we run this again. Okay, and we're just printing the lines. Okay, that's a very complicated example to show how complicated Zig has made opening a file. But anyway, it's explicit at least, but it's still very complicated how the new interface is. I think most people are just going to make helper functions for this because they don't want to deal with writing this stuff every time they want to open a file. Anyway, so that's a good example of when you want to actually allocate. And let's say, for example, okay, one good example that's simple would be prime numbers. So I'll write this quickly. No, it's not a function. If is prime, we should be in brackets. We go prime numbers dot append with the allocator with I. And we call try on this. Let's see if there are any errors. Okay, there's no errors. Okay, and then we call get prime numbers. We've done that. Let's do this and see what happens. We get an error. Leaked. Memory leak. Why is there a memory leak? Okay, so I think we need to de-init this. So we just defer prime numbers dot de-init with the allocator. And that should get rid of the memory leak. It did. Okay, there we go. That was fine. So, as we don't know how many primes there are, let's actually print the length as well. So we're going to debug print, do this. Let's say, I don't know, primes found. It was that equals prime numbers dot items dot len. That's how you get the length to an array list. And we'll write this down. Okay, so we found how many prime numbers? 168. Don't know if that's correct. I'm guessing it is. So 168. So this is a good example because I didn't know there was 168, so that's why I'm using an array list, because I don't know. And you need to allocate because you don't know how big it is at compile time. In theory, you could make it 1,000. You could get, a buffer of 1,000. But say if you went for 1,000,000 times, you'd have to, you have to allocate in that situation. Anyway, so that's how you allocate. And I'll show you, for example, so the debug allocator. If I take this away, it will actually detect the leak like this. See, it detects the leak. Memory address is it leaked. If for some reason it says error GPA, even though it should be, it's renamed to the debug allocator, so I don't know why. It's anyway. That's just, we didn't get rid of this, so. Because all the debug allocator will do basically is whenever you de-init it, if something isn't freed, it will tell you and give you a panic. But what I can do is I can show you certain things. So let's use the fixed buffer allocator for this. So for example, we could, so I'm just going to comment this out. So this should in theory still work. So we're using the fixed buffer allocator. I actually learned something new. You can actually write the type here and then use dot, which I didn't know you could do, which actually helps quite a lot. So I'm just going to link the fixed buffer allocator because I don't like writing the whole thing. Fixed buffer. That means I can actually write array list here. Let's do this. Array list. Then I can see the type where it's supposed to be. Use size equals dot try. I like that. That's pretty cool. All right. So this should work still exactly the same. Let's see. Okay, we have got out of memory. You know why? Because we're only using 1024. It's not that big of a buffer. This is generally why. So say the file's big, or maybe say 1,000 numbers is probably bigger than this. So let's make it, I don't know, 5,000. I don't know what that would be times 2. So it's a multiple of 2. See if that goes out of the bounds of the array, of the buffer. I didn't. Okay, that worked. I don't know how much we allocated though. Also, I didn't de-init it, so let's de-init the... Alright, okay, I just realized, yeah, you don't actually de-init... So the fixed buffer allocator uses stack memory, so I don't think you actually de-init it ever. You do de-init this, so that's fine. Then I can use my tracking allocator, which actually be very useful in this situation. So first I actually need to bring the tracking allocator in, and then we comment this out. Hopefully we don't get any errors. And then what we can do, at the end of it, we can call here. So we have tracking allocator here, dot print stats. And we can print how much we've actually allocated. Okay, 1,688 bytes. And what we can actually do is test if it, frees or not at the end of the scope. But yeah, anyway, that's my tracking allocator, which is very useful. It shows how many bytes and how many allocations. So we had 1,688 allocations, which doesn't make too much sense. How was that many? Sorry, allocation count 1. Right, okay. So I guess it doesn't work with append. Because we're putting the allocator in with append, it doesn't work. That sucks. That would be very useful if it did work, but apparently it doesn't work, which sucks. So there's different allocators. And the tracking allocator doesn't really work with array list too well, but it does work with everything else. So for example, if I wrote something like this, let's say const buffer, which is a U8 slice, equals let's say allocator dot create. Would it be alloc? Sorry, allocator dot alloc. Comptime t would be a U8, and the size would be, let's say, 10,000. And then we need to defer buffer or allocator dot free any type buffer, like so. And we're using, so it should, okay, we've got a try. Yeah, we're going to use try. Don't forget try, because it can return an error. So now it's 11,688. Why? Because we just put on 10,000 bytes and we allocated twice. Anyway, yeah, so that's my tracking allocator as well, which is quite useful outside of array lists. I'm not sure if I could get that to work with array lists, but anyway. That was an example of using different allocators for the same thing. What you could also do is just simply, the simplicity, just take in an allocator here. Allocator. And we're just going to copy and paste this. Do this. And then let's pass in the allocator. And then we can't have the tracking part. But we can do it here. Tracking allocator dot print stats. And then do this again. So it just kind of makes it a lot simpler, because generally what things do is they just take in an allocator, and then it doesn't matter what it is. So is it a fixed buffer allocator? Is it a page allocator? Is it a debugger? It doesn't matter. It uses it. It uses the memory like normal. So you only really need to create the allocator normally once. Okay, free count 2. Okay, everything's fine. So there's no memory leaks, which we knew already because we tested that. But this means we could, you know, comment this out, comment this out. Also comment this out. And then use the fixed buffer allocator, which obviously you need to be careful with because it can go outside the bounds of the array. It goes out, could stack overflow, sorry. And we got out of memory. You know why we got out of memory? Because we allocate 10,000 bytes on the heap. Let's get rid of that. No, we won't go out of the bounds of the array. And that's fine. So you can basically just pick and change, swap and change these. Which is kind of like, it's like dependency injection allocators in Zig. You just put in whatever allocate you want, and it's just, it's basically just a vtable how it works. It's like an interface. Anyway, you can create your own allocators as well. They basically just work with a vtable. Because I can show you my tracking allocator, it works through a vtable. So basically you've got these 4 main functions. We have reset, alloc, resize free. Reset isn't one of them. So here we have remap, alloc, resize free. You create those functions yourself, and then you set it in the vtable, and then you've created your own allocator. It's basically like, because that's what an interface really is. It's just a set of function pointers with a name. And this is just a function pointer. This is a pointer. If you look here, it's a const function pointer to only opaque, U8, alignment, usize, and it returns an optional pointer. Yeah, anyway, basically that's what it is, or alloc. So yeah, it's basically just, it works like an interface. But the way mine works is pretty much, it's really simple really, because it just adds the bytes. If it allocated correctly, it adds the bytes. Anyway, those are allocators. Next part. Alright, now we're going to look at Comptime, which is probably one of the most misunderstood parts of Zig entirely. Because people think it's like, you know, you could do anything you want. You could basically just run an entire program in Comptime. You can't. Sorry, you can't. I can show you that. I have a program somewhere that I don't know where it is, but I can try and find it. Alright, so here I have... so I created a tic-tac-toe game. And I have this thing... Right, basically I just run a load of perfs, like just play a load of moves, count them. That's all it does. But if you look here, it says error. Evaluation exceeded 1,000 backwards branches. What does that mean? It basically means that you printed too much. You looped too many times. It can't... So the compile time is not going to print for... Because literally, how compile time works is it generates code. And there's a limit, and it only has 1,000 branches limit. You can't just, you know, loop forever. An inline 4 would basically be these are all compile time depth, compile time. So everything's here is comp time, and I have the inline 4. The thing is, yeah, there's 1,000 limit, so you can't loop over 1,000 times in comp time. So it's not, you can't just run an entire program at comp time. You can't do this. It's not what it's for. It's generally for, so it's for platform-specific code. So say you want to generate something for Windows, but you don't want to generate something for that. It replaces compile time macros in C. So you can generate code. You can call functions at compile time, depending on which operating system you're on. It could be, for example, what is a usize? So I'm pretty sure usize will use the comp time to say if it's 32-bit or 64-bit. It's also used for generics. So I'll show you, for example, we've got array list. So array list is a good example. So ArrayList takes in a Comptime T and returns an aligned, which again takes in another Comptime T. So this is basically, this T is a type, which basically means you don't know and it's generated at compile time. And what the compiler will actually do is it will make a load of code depending on whatever functions you call. So if you call a load of functions with generics, it will generate each individual type that you make. That's what generally what Comptime is for. It's not for running, endless amounts of code at compile time and then just running it. You may as well just pre-compute at that point and then just make it a constant. Anyway, so yeah, let's give you some examples of Comptime. So one of the main words, so say for example, I showed it before, when you want to print something. So say you want to print something, and then here we're just going to write FMT and any type, args, like so. And these probably need to be Comptime, otherwise we're going to get an error. So it doesn't actually give us an error because we're not calling it. So it's very lazy, the Zig compiler, so I'm just going to call this with, I don't know, hello world and nothing. And say it's going to give us an error, unresolved Comptime value. So we make this Comptime like this, and it's fine. And then we're basically calling print with print. But that's to show you what it's like. So it has to know what this is at compile time, because basically this is the format, right? It has to know what that is, and the args it can work out itself. So obviously this runs and it will just print, print hello world. But you can make it so like this is kind of redundant. So you can make it print string, for example. Get rid of the args, and then make this blank, and then you can just call print string. And get rid of the args, and then you don't need to use spam this empty. If you just want to spam like print a string, you don't need to do that, but you need to use Comptime for this. All right, so let's say make some generic code, or what you can do. Say we want to use an add function and we don't know what the type is, so let's go add. So we're going to go Comptime T is a type. And then A is going to be a T, and then B is going to be a T, and then this is going to be a T, and it's going to return A plus B. And then we can just call this, let's say, just say add, so we want const, we need to put the type in, otherwise, because it doesn't know what it is, obviously. So I think we can just make it so number, say result or whatever, result i32 equals add, and we need to put the type in, so it's an i32 and say 10 and 10, debug print. We could also do something like this, so let's say print var, so I don't care what it is, just print it. We don't need FMT really, because this is going to be blank. And let's say new line, print var new line. We don't need FMT, we just need the type, so let's say any type, and it's going to return a void, and we're just going to call debug print this with a new line, and then variable. That should work. And then we're just going to here be lazy and just print var new line result, and hopefully that works. There we go, 20. That works. So printing any type. I'm not sure if this would probably break if it's a slice. So if you put a slice in, it will probably break because you're not using the S slice. So that would be a problem. Anyway, so then we can say, I don't know, let's make it const small result. Result. There we go. So this is just like really simple generics, just using any type and then Comptime T and then T, and then you put the type in whenever you call it. That's really, really simple generics, and it's very, very simple in Zig to do this. So So I'll show you a linked list. So a linked list is quite a complicated piece of code. It's not that complicated, but it's a good example to show you generics. And what's called, it's called an anonymous struct or a generic struct. All right, so here's my linked list. We're using a tracking allocator just to see how many allocations there are, or how many bytes there are, which I'll probably have to put test linked list. I could send the tracking allocator there, but I don't feel like doing that. Anyway, so I'll show you the generic linked list. I'll show you the regular linked list. So I created an i32 version. So create linked list i32, which creates this linked list i32, which has a load of functions like append, assert, insert, remove index, print length. Basically it. And it's a node i32, which is again just here, data i32, and the pointer to the next node. And it's nullable. So if it's null, you stop, basically. So you create this. Of course, you also need an allocator because it uses because it doesn't exist. It's a pointer. I mean, you could put it on the stack, but no, it's not. You can't really put it. It's just dangerous to put it on the stack. You normally want to, you want the things to persist afterwards. So append creates node, which will actually catch unreachable. It probably should return an error, but it's catch unreachable because it's just, if there is an allocation failure, we should probably just panic anyway. So it's, it's not that bad to do this. But I'll just show you, for example, how you make this generic. So I have this one, which obviously an optional pointer to node i32 and a length usize. And the generic one, it's a function. First of all, it's a function, and it basically returns a list or linked list, Comptime t type, and then returns a type. So it's kind of like you're returning a struct, if that makes it. It's like a function that returns a struct, and the type is generic. And it takes in the Comptime t of the type, and then we just put the type here. And then, because we don't know what this actually is, we have to use this at this, so we know what it is, and then we just use at this. And then basically everything is exactly the same as it was before, except every type is a t. And that's basically it. So this function is that. So if I look at append in either one, so linked list 32, so we have node i32, node i32. We basically just replace all of this code. It's exactly the same, except for we replace this with node t, and the rest are the same. That's basically it. Otherwise, it's just a generic linked list, and that's it. So this is what we call an anonymous struct or generic struct, where you create the struct based on some generic thing. It could be based on maybe a union, and you select what's in the union. So you can have, for example, I think ArrayList works like this, or you could have something like, I don't know, you have a struct that could read a file or write to a file, or something like this. So you can make it generic with using this kind of thing. So you don't have to write something twice. You could write it once and then have it do different things depending on the settings. Okay, so test list is the thing I need to use. So I'm going to import this. All right, so we call this test lists, and we're using the i64 version. Yeah, U64 version. So here is the results. So 100,000, 200,000, 300,000, then null. So we append those, and then we print. And then we insert 0. Do we insert 0? We insert 0 at the start. So we insert 0 at the start, so that inserts it. But you can also make this any type. So in theory, you can make it a linked list of anything. So you can make it a linked list of a struct, and we can mess around doing that if we want. So say, for example, we could have, I don't know, let's make it an enum, just to mix it up. Let's try this. So now, I don't know if we'll get an error. We didn't see an error, so yeah, there we go. So now it's not, now it's there, enum. So this is generic. And this isn't actually that complicated in Zig to do. Depending on the code, some code could be very complicated doing this. But this is generally the use of Comptime. I'll show you another use now. So a few things I haven't mentioned. Say, for example, you want to work out what something will be at compile time, but make it mutable. So we can do that. Let's say, for example, we would want to have an array or maybe a value. Let's say, for example, we want to count the numbers or letters in something. Is val. And then we could just call here. This is what we called it compile time. So I'm actually going to just print the var, because I can't be bothered. So print var, new line, val count total. Expected found usize. Is it a void? So it should be usize. Okay. It doesn't give me any errors, so I think this will actually work, but we'll see if this works. There we go, 16. Is that correct? I just counted them, there are actually 16, that's correct. So this all happens at compile time, right? So now this is a compile time known thing, and because, for example, const is known at compile time, we know the length of message at compile time. We also know we can use an inline while because we know the length at compile time. We know this at compile time because it's there, it's written, we know it. Well, the things you can't do at compile time are things like calling the operating system. So if you ask for memory, no. If you ask for user input, no. If you try to open a file, no. You can't do any of this. Basically, it has to be within the program. Anything within the program you can do at compile time. It has to be accessible and not known at runtime. It has to be known before. As this is const, we know the size. We've set the size. And the comptime var basically says it's mutable, but it has to be known at compile time. And this is what an inline for will actually do, is it will basically write it out by hand, each loop. Which means there is a limit. There's a limit of 1,000, which I've already shown. But yeah, so basically we've called this at compile time. We've generated this, and maybe we can make this, a global constant. Obviously not great to use a global variable, but it doesn't matter because it's const, so it doesn't really matter. And this will do the same thing. There we go, 16. So you can do this at compile time. This is generally the power of Comptime. It's about generics. It's about say platform specific code. I'll show you some platform specific code as the last example. It's about generics, it's about platform specific code and things like this, and calling functions at compile time. So here's an example from the references. So here we have built-in. We get the built-in, which is an STD thing. And then we have const separator, which will be a char. And the separator will depend on if it's Windows or if it's Mac or Linux. So here, this will be set at compile time. If it's Windows, we use this. Otherwise, we use that. And that's simply, so it's specific code. You can also do things like, CPU architecture, depending on that. Things like this. So that's generally what the use is for compile time. It's not used for running lots and lots of code for performance, because there's 1,000 loop limit. All right, so let's do the build system, shall we? So the build system is quite complicated, honestly. It's one of those things that you kind of just I try to avoid it as much as possible. All right, so how do you use the build system? So we have this project here. Let's go to the folder. So we have this folder here, right? It has these files. And say we want to make this into a project. And why would you want to make this into a project? Well, you can link libraries. You can have caching. Maybe you can compile for different platforms. But the problem is the build system is very complicated and kind of, not that beginner friendly. But if we type in Zig, we have here Zig build, exe, build live, build object. And we have Zig init, which initializes a Zig package in the current directory. So unfortunately, when we call Zig init, so we're going to call Zig init here, and it will create this for us, and it will create a lot of stuff we do not need at all. So if I go back into here, it's now created build.zig, and build.zig is full of a load of comments. It's created Zig 2026, that's fine, I guess. That's the name we need. We have artifact run step, run the app, that's fine. But then we have args, we add args, that's fine. We add a test module. Why are we adding a test? I didn't add a test. And then we go to main. And we have this, which it's run loads of tests. And it also has root. So we're importing a library called root. Why are we doing this? We don't need it. So what I'm going to do, I'm going to delete main.zig, get rid of that. The problem is every time, literally every time you do this, it will generate the same code, and you don't want it. You don't want it. So I'm going to move this into source. Move. We're going to also remove that. So we're going to move that to there. And we're going to move that to there. And then I'm going to copy and paste what I normally copy and paste. So I have this file saved called build template. So this literally just gives me the only thing I need just to get it to work and use the main file. That's all I want. Just use the main file and leave me alone other than that. So copy and paste this into the build.zig, paste it, and then change the name to, say, Zig underscore 2026. There we go, that's done. And then this works. So we can close this, we can close that. And now this will basically do exactly the same as it's already done, but we're now going to use the build system. And how to use the build system, so instead, the command we were using before was zig run main.zig. In this situation, you don't do that, you just say zig build run. And now this will, the first time it runs, it'll be slow. There we go, it runs. And then you run it again, and it's ridiculously fast. Why? Because it caches. It caches everything. If you see here, we have Zig cache, which caches basically everything. Sometimes the program can be very big when it caches. We also have Zig out, which creates the exe. Well, that's the build system very simply, because most of this stuff is actually pretty complicated. You have the target, optimize. Like, some of this is really, really complicated stuff as well. Generally, I just copy and paste this and just forget about the build system. Because you can also like import library. It's really complicated. I've never really seen like a good tutorial about the build system, so I just avoid it like the plague most of the time, and I just use it for when I want caching and things like this, and I just use it to build big projects. But otherwise, I basically ignore it, and I don't like using the build system at all because it's overly complicated. I don't know how any of this stuff works. I don't need to. I just copy and paste this every time. Anyway, so that's kind of the build system. The problem with the build system also is if you want to have run tests. So I'll show you tests quickly. And that's called defer. I should run. There we go. So that runs. Okay, so if you see, when we're not using the build system, it's very easy to just call test. So we literally just called zig test main.zig. That's all we need to do to run a test. So yeah, that's pretty simple, and it just passes. So if it fails, like if you don't allocate enough or it gives you an error, then it will say fail and won't work. So that's testing. They're pretty useful outside the build system. Because if you ask me how to do it in the build system, I don't know how to do it. I'd basically have to look it up. Honestly, life is too short to use the Zig. Maybe there's someone who knows how to use the Zig build system and you can watch their videos. But I'm just going to avoid it like the plague. Because honestly, generally what I do to avoid tests like hell is I just say, for example, I'd instead turn this into a function. Because I'm using the build system, I just don't want to deal with this. So I'm just going to call this test allocations, like this. Make it, I don't know, error void. We're going to copy and paste all this, get rid of the test part, get rid of this, get rid of this. And we've got test allocations, so let me just run test allocations with try, like this. So what I'd probably do is do the run tests. And make it an error void again, and then call try test allocations from there, and then just call run tests. And then if I don't want to use this, I'll just comment it out. There we go. I don't need to use the build system now. I don't need to call anything, and that does exactly the same as I just did. And I just comment it out, and I don't need to use the build system. So maybe I'm just too lazy to learn how to do it. Anyway, you can probably watch someone else's video on how to do that, because the build system is just not really beginner friendly at all. So I'm just going to avoid teaching it in this tutorial entirely. Anyway, that's if you want to make a project, and I'll put this in the description so you can just copy and paste it. we'll put it in the description. I'll put it in the GitHub. Alright, so I'll quickly go through optimization modes. So in the build system, it's actually not as complicated as it seems. So if you click here, we have standard optimize option. You can click that, and we have standard optimize option options, which basically links to optimize mode. So with the language server, you can simply just type in dot preferred this, and then dot, and we have debug, release fast, release safe, release small. So debug is obviously for debugging. It gives you all the safety features, has bounds checking for arrays, it has like integer overflow checks, things like this. Release safe will be a lot faster, but still have some safety features like bounds checking and things like that. And release fast and release small will have no checks at all. So I'll just show what this is like. So we do this, hit save, and then I don't even know what this program's doing nothing at the moment. So okay, Zig build run, and this will run it in the release mode we set. Vowels. I believe that will create a new so if you look for Zig out, apparently it doesn't. We can compare the sizes. So if you don't want to use the build system and you want to do that, it's basically the same thing, but we just use a different command. So say for example we go into, let's go into source, right click and control shift right click and do this. So we have Zig main, Zig. We have the commands, we have build exe, so we're going to go Zig build -exe. I'm going to make this big so you can actually see what I'm writing. Main.zig, and then we go -o with the capital, and then whatever the build, so you got debug, release safe, release fast. Let's say release safe. So that creates an exe here, main.exe. We can create a folder for that as well. Release small. We can compare the size. But the thing is, it's not going to be much of a difference in size because it's very small to begin with. It basically does nothing but print anything, print some one thing. Yeah, it doesn't even have that now. But we have this, which is about 527. And this is about 12, so it's tiny. It's absolutely tiny. That's generally what I do. Like, I mean, you don't even need to use the build system at all, because yeah, it's a bit more complicated to use the build system. But generally, just do this like that, and then dot something, dot fast, dot small, whatever you want. All right, so that's building. All right, now I'm going to go through a few kind of, I guess, things that Zig is strict at. So I'll just delete everything here. So one thing that Zig checks a lot is a thing called Zig integer overflows. So say for example we create small number as a U8 and we make it 255. And then we do like var, so we actually mutate it. And then we can go small number plus equals 1. What do you think is going to happen when we do this? And then we're just going to print small number. Let's just check we're on debug mode. We are. So we can, on this one, Zig build run. Panic integer overflow. So this is actually done at runtime, so it won't be done at compile time, which is interesting. Because we didn't actually run the code, it won't actually catch this. But maybe if we make this a comp time, it will catch this. So if I do this, it will catch it, yeah. Overflow, integer overflow, type U8 with value 256, which is overflow. Because if we look at bits, you kind of need to understand bits to understand this. So basically when it's 255, that's all of them added up. Because we have 128, 64, 32, all these adds up to 255. If we add 1, what happens? It goes to all 0, and the value be 0. This is called an overflow. And obviously it kind of deletes data if you do this. If you have data and it goes to 0, 255 to 0, you've lost stuff. So Zig tries to stop this. It tries to prevent you from doing this. It depends on the size as well. You can also have an underflow. Say if you have, I don't know, say you have 0 and you go minus equals 1. This will be overflow. Type with -1. You know, it's gone underneath the value. So that will basically reset the bits to full in that situation. But what you can do in Zig, if you want an overflow for performance reasons or something like this, you can use the percentage sign, and it won't care. Now it will say 0 most likely in this situation. Oh, sorry, we'll say 255. I'm pretty sure. Wait, we don't need this one open. In this situation, it's probably going to say 255. Yeah, 255. So when you go -1 from 0, it basically sets all the bits to 1. So we've gone from 0, 0, 0, 0, 0, 0, 0, 8 bits. When you -1 on this, it simply sets them all to 1. Because it has to. That's how it works. So this minus equals 1 equals that, which is 255. So 0 minus 1 is 255. This is just how how computers work at the bit level. So when there's an integer overflow, Zig basically tries to stop you from doing it, but you use the percentage sign to not care, basically. If you say, oh, if it's 255 and I plus 1, I don't care if there's an overflow, which the only time you really want to do this is for performance reasons. So it goes from 255 to 0. So you could literally say something like this, that, and then do this. So we go value before, to show you how stupid this is. This is just how computers work. So it says 255 plus 1 equals 0. That's why you stop integer overflows, because it's kind of stupid. Obviously that should be 256, but 8 bits aren't enough. There aren't enough bits there to represent this value. If you made it 16, it's absolutely fine and there's no problems. So if you did this, it would just say 256, because there are enough bits to represent the value. Those are integer overflows. What else could there be? Conversions. So sometimes you could truncate things. So I'll give you an example. So here we have, let's say, 16, U16, right? Let's make it like this, const, get rid of this, be like that. So it can represent the numbers. That can actually, and it's compile time known, so it's fine. This can actually represent it. And it'd be fine, 255, 255. But if we make this 256, what do you think is going to happen? If we hit save, I'm going to say type, error type, U8 cannot represent integer value 256. Alright, so this value here, instead of 255, we'll make it 256. So obviously, like, this will just be 0 if you do this. So if you truncate it, you just basically take away the bit at the end, which would be 256. And then this will be 0. So if you print this, this should say 2550 or 2560. Yeah, there we go. So basically it just cuts that bit off and just uses the first 8 bits, which makes it 0. We've deleted data. This is why Zig is very strict with this. If you delete data, then you have problems. Also, if it's not compile time known, it will also have problems. So if I do this, var 255, small number, plus equals 1, it's not compile time known at this situation. So it's going to have problems. Okay, so it says found U8, found U16. So because it's not compile time known, the compiler's like, this could be deleting data, we don't know. So I'm just going to, if we make it comp time, it will actually know. It will know. So it can't represent 256. But if it's not comp time, that means it's runtime known, and it doesn't know. So basically you have to use truncate in this situation. So at truncate, you have to do it. Just because the compiler isn't entirely sure, so just going to make sure. I believe this only works on debug release safe. Let's say, for example, we do this. And let's set this to, in the build system, .u equals .release safe, or release fast. Okay, apparently it still doesn't run. I'm not sure exactly why that is. Maybe it's something to do with the build system. In theory, it shouldn't. So let me try running it with release fast inside source. Let me run it from here with release fast. Okay, Zig Builtins. You want to go Zig run, maybe? Zig run release fast. It's still doesn't work. Okay, that's interesting. I thought it wouldn't work, but apparently it's strict anyway. So we need to use @truncate. Because there are some, like for example, bounds checking. It doesn't have bounds checking in release fast, just for performance reasons. Anyway, so we have to use @truncate when you make a value lower. But generally, you don't normally need to use lower bit sizes for most things. It's only for maybe like really niche performance situations. Most of the time, you're going to use i32 or u64 or usize or something like this. But it's very strict in this situation. So you can also do bitwise operations in Zig. And bitwise operations, Zig is so strict with them. So we have like things like bitwise and. I'm not sure if I have a thing that will print the bits. I can just generate one quickly. Alright, so I've just written a function that will print the bits, which is a bit complicated to be honest. But basically, say for example here we have value of 1, it'll print value 1 and show you the bits in, I think it's little endian format. Say for example we make it 10, we should see, yeah, that's right, so it's like 1, 2, 8, 4, 8. So 8 plus 2 is 10, that's basically it. So say for example we do, we're going to print the bits. I'll show you how this works. Value is 0. How's that possible? Don't know. Ah, that's why. So basically what AND will do is every bit that is the same, it will basically set those bits to the result. So here, these bits are set, these bits are set, these bits are set, these bits are set. So they're not the same, so it's 0. But if I make this one, I don't know, 255, then it has to be, it will set the basically to 10. Because this is the same, this is the same. So in the result, these are the same. That's an AND. ANDing is absolutely fine in Zig. There's no problems you'll have with it. You'll have a problem if you have a different size, though. I've had problems where you do this. Generally, but it's probably not going to give me problems now. Because of Sod's law, it's not going to show me the errors when I want to show them. But I have had problems when I'm using AND. But say we use bit shifts. What is a bit shift? I'll show you. Say we have const A, let's say, yeah, const B equals, let's make this 1. I'll get rid of U. And I'm going to say equals A shifted by 10. That's probably too big. So I'm going to shift it by 5. So this basically is going to shift that number 5 bits along. So we have here, we go 1, 2, 3, 4, 5, and then the bit is set to 32. That's what shifting does. But the problem with bit shifts are Zig is very strict. I mean, it's extremely strict. It's like ridiculous how strict it is. If you say, for example, const, I don't know. Apparently this doesn't mind that because it's a usize, I guess. But if we make that outside, it basically has to be within the bounds. And sometimes Zig will actually specify, this must be a U5. And it's like, what do you mean a U5? It means a U5? It's just like weird. But say, for example, we make this. I'm going to switch these to U8, just for simplicity. And we're going to make this 255. And then we're going to shift this by 1. And this should be an integer overflow. So it's not going to work, I'm pretty sure. Apparently it did work. That makes no sense at all. Okay, I'm confused. That in theory, that Zig should not allow that because I'm shifting something and making it integer overflow. This is also an i32, so I should probably print a U8. So we have 8 bits, right? And say we have a 1 here, and we can shift it 7. So that's why it's basically saying it's a U3, because so it's expecting a U3, but the problem is it can't shift it by 255. It can only shift it by 7. So it basically has to make sure that the bit shift is in bounds. I believe, I'm not sure if you can do this. Let's have a look. So can you percentage? No, you can't. Apparently, this bit shifts are very strict. So we can make this 7, and it's fine. So it has to be within the bits, the amount of bits. It can't go over that. So we can shift it 7. And that shifts. It basically integer overflows when you do this. But say if we make this 1. If I actually click something, make this 1, then we'll shift 1 to that, so it should be 128. There we go. I mean, yeah, anyway, so bit shifts are very strict, but generally you don't need to use bit shifts anyway for most situations. So in this we have quite a few useful built-ins. So we have type info, type of. So it basically tells you what type something is. And then we have type info, which basically can tell you what it is. So you can also say like if this is not an int. So you can say like if this is not optional or not an int or not an error union or something like this. You can also get a bit count by info.int.bits, so it tells you the amount of bit counts inside this. We also have int cast, which basically will cast it into whatever it needs to be. So will cast a bit count, whatever bit count is, usize into an isize. And here we're int cast is generally what you want to use for integers if you're casting. There's also as. You can also use as if you want. So you could do something like let's get rid of this. Let's say we have const b equals as, and we specify the type. Let's say u16, then a. So now this is we've casted this into a u16. Even though we don't really need to use as, we can simply just write u16 here and just get rid of that, and this will still work. So it's not really necessary to use as, but there it is there. Of course, I've showed you before, there's panic as an inbuilt panic, but you can basically just type in at, and it tells you all of these. So we have memcopy, which can be useful. I was trying to show you memcopy. So we have use at. So it needs a pointer. So memcopy needs a pointer. So you put a pointer to it. Will this actually run? Let's have a look. It will not. The formatting's wrong. We need to put any because it's an array. There we go. So basically we just copied all the values from array A to array B, memcopy. You also should be careful because if you do something like this, not matching lengths, yeah, it'll give you an error. So you have to make sure they're the same length because I believe memcopy will require a slice. It won't just take in a pointer. All right, so memcopy has to be a slice. Basically, it has to have a length. Otherwise, just why are you doing this? Just set b equals a. You don't need to use memcopy. Just use b equals a. The memcopy is there for slices or arrays or something with a length. You can't use it with like individual stuff. What else do we have? Bitcast will actually literally catch the bits. So if you say, for example, you create a float. Let's say f32, value f32 equals some weird number like this, and let's say converted value equals i32 equals at bitcast value, and then we print those, not print the bits. Well, you can print the bits if you want, that might be interesting, but the thing is it's a floating point value, so the bits will be weird. But we can print the bits of converted value. Alright, so we have the bits and we have this weird value. The problem with like floating point numbers is you shouldn't really convert them from integers to that, but you can just cast the bits if you want. As if all you care about is the bits, then yeah. But the thing is the value is going to be garbage if you convert from float to integer. It's just not, unless like you put it, we have int from float, which will truncate the values. So we're probably going to get 1 2 1 2 1 2 1. There we go, 1 2 1 2 1. So basically it just deletes the zeros at the end. So these are very explicit in Zig. So you have to use int from float. If you also create an enum, for example, and we want to get the value, which will probably be 0, we have to do. I'll get rid of this. Get rid of that. What we can't just say, for example, equals example. That will not work. It will say expected and found a main. It was like, what's this? How do I do that? To convert an enum to an integer, you have to go at int from enum, like so, and then it'll work. And this will probably give you value of 0 because it's the first value. So value 0. Also, I'm not sure what I said before. If you want to set the values, so you can set the values like by setting an internal number. So you can make it like u32 or something, and you can say a equals 100, b equals 200, and C equals 300. You can set the values like this. Then we can say convert it again, and then here this is going to be 100 because it's A. So value is now 100. All right. So yeah. So you can also do it the other way. So you could say, for example, I'm not sure if you can go enum from int. In theory, it should. I'm not sure if the values are checked. We'll have a look. So yeah, there's example.a. So that does actually work. But say if we make it a value that's not in that, it's probably going to give us an error. Yeah, it has no tag. So it basically looks to see if it's one of these values. If it's not, then it's not going to work. You can't convert it. All right. So so it's int from enum. So there's loads of these, and there's loads of these. You can basically just type in @ and it gives you loads of things. Bit reverse. So we have float cast, if you want to cast into float, float from integer, int from bool, int from float, int from pointer, lots of these things. Mem set, it will set the values inside a slice. Min will basically just give you the minimum or maximum. Round, so there's lots of maths things as well. Tag name, this is used again for most. You can actually use this for. Let's see if we could do this. You can say const. Alright, so here we have thread panic integer overflow in file main in function safe add u8 255 plus 1. So we can actually have full debug information. Like we can get the name of the file and we can get the name of the function using source. Of course, you could just write that yourself, but you can in theory just use this anywhere, and you don't need to write it. So you could just write get function name like this. And then you can print out stuff like that. So you get detailed debug information. So those are some built-ins. But yeah, I don't use every built-in. I mean, I rarely. You mostly just use them when you need them. But most of the time, you're going to use stuff like you can use type of, you can use @this. You're going to use things like conversions. Is most of the time what inbuilts you're going to use, what built-ins you're going to use. But I thought I would show you how to get console input. It has changed quite a lot through recently, because here we're using fsreader stdfs.file.stdin.reader, and then we have to create a buffer first of all. We create a buffer, and then we get stdin.reader, get all this, and then we get the IO reader from the stdin.reader interface, and then we can use line, which I believe is, I should probably write that as a u8 slice. Take delimiter exclusive, and basically all I want here is just wait until I press enter to exit. Press enter to exit. But you can also use it to get console input. So I'll just show you doing that quickly. Alright, so here I'm going to show you how to get the arguments, so command line arguments. So we have to use the allocator for this. So we use args, which will be kind of a pointer to. It's basically like this. It's a slice of u8, how it is. But apparently it's u8. I don't even know what this means, to be honest, what that means. So basically when you put this in, so say if we go, so we have to build this. I've already built it. Let's build, and then we have to go to the exe that it's created. Backward space dot zig with a capital Zig _2026. .exe, and then the command line arguments would be just hello, this is an argument. Don't even know if you could do this. There we go. It just prints out hello, this is an argument. So command line arguments. There we go. That's how it works. Alright, so let's work on console input. So I've written this for us. So, I mean, Zig has made this very complicated now. Even the problem is, like, if you just want to make this a function, get reader, it will not work. If you do something like this, get reader, we put in slice of u8, and then we comment this out. Or say we comment this out, and then just type in, comment that out, and go equals get reader. We're going to get a seg fault, because of course we are. So we're going to get a seg fault from this. We don't use @ because it is that. Okay, I'll show you this. So segmentation fault, index out of bounds. Basically, the problem is this will be stack memory when you do this. So you basically can't even do that. So we can't use getReader at all. We have to basically put it all. There's no helper function you can use. You have to get std in from this. You have to get the reader from this. Then you have to get the interface from this. All like that. And there's no way to shorten it that I've found. Anyway, so we do this using this buffer. And then I've got this while loop. So we write something, debug print. We could use the writer, but that's more effort. I'd rather just use debug print. And then we get the line from getLine, which I've used a helper function for. So we have const line equals reader.takeDelimiter exclusive, which basically goes until we have this. And this is for, I guess, Windows, because Windows will have this return character, which is really annoying. I mean, for Linux, you could probably do like this, I guess. Something like that. But I want to, it's for Windows, so I'm going to do that. And then if it's an R, we're going to toss, which basically just skips this character. Because if you don't do that, I'll show you what happens. It basically just prints forever. Run. Helps. So write something, let's write hello. And it actually just spams forever, right? The reason is it basically finds the next character is a new line and keeps spamming new line over and over again. Doesn't actually skip past it. So you have to manually skip past it, like so. So we get the next char with peak. We see if it's this return character in Windows. If it is, we toss it. We see if it's a new line, then we toss it. And that's how you write it. So let's get line. And then we just call get line. We see if it's closed using stdmem.equal. Which basically just compares slices and see if they're the same. And then if it's not, then we type it. So I'll show you this. So write hello. You write hello. Right, close, it closes. There we go. That's how you get console input. It's not exactly the most intuitive thing, but I guess you just do this once. I'm not sure if you can make this a global variable. I'll try to experiment making these global, because that would actually help a lot. I don't know if you can do that. Apparently there's no errors. It would just annoy me that I have to spam this. Write something, hello. So making it global does actually work. That's fine. But you do have to set it at some point. So maybe you just set it at the beginning of the program to this. What I'd probably do is make this global, set it at the start, and then just pass around the same reader, just so I don't have to do these lines every time. And then have getLine as some kind of helper function somewhere. That's what Zig probably should do, is have some function that says getLine, so you don't have to deal with this stuff, but, you know, Zig likes to be explicit. So that's how you get console input. If you want to get individual characters, you'd use I'll show you. For example, you have reader, you have reader.getByte, peak byte, or take byte, which basically will get the next byte, meaning next U8. It'll get the next character. And you got to try it. So it takes the next byte. Or you can read until delimiter, which basically means read until this character. If you're on Linux, you probably make it, you know. So you could make it, for example. So here we got some compile time code. So here I got const delimiter. Basically, if it's Windows, we're going to go until this. If it's not Windows, then we go until this. And then I guess we check here. But yeah. I don't know if you need that for non-Windows, but I can't be bothered to put an if statement there, so it's not really, you know, a problem. So yeah, I'd probably just make a helper function if you want to get the line like this, and then use this as global. Anyway, that's how you get console input. All right, let's show you the ridiculously complicated way of using console output without using std debug. All right, so here we create a buffer. Then we get the writer from std.fs.fileout.stdout.writer. We put the buffer into that, and then we get the std out from, which is an stdio.writer equals at stdowriter.interface. All right, then this comes to here. It puts the writer into the function and std.print, and we have to flush. Flush will basically, I guess, reset the index so you're not overflowing the buffer eventually. But that's the really complicated way. So it's not that complicated if you just get the buffer once. If you get the writer once and then just reuse it everywhere, it's not as bad. But yeah, it's pretty tedious to do this every time. So create a buffer, create the writer, create the std out, and then use write, and then also the write will actually cause an error, so you have to use try, and you have to make everything return errors, or use catch. It will mean you have to handle errors, but it is the standard way of printing. So generally what I would do is just create this once, and then just pass it to every function you use, if you're going to write anything. So if you're going to write anything, I'll just pass the writer. So in this function here, we have std out, just pass this everywhere you want to use it. You could also include it in a struct. You could be really lazy if you want and just do something like this. You could say public. So yeah, so you create something like this, like context, and then you could just pass this to every function you want to use it. You could also, in theory, create the reader here as well, and use that. So then you just pass context. So say, for example, you want to have a function that prints something. So you go, yeah, defer context dot free heaps, guys. Alright, so yeah, this is basically just really streamlining it, really. So, I mean, the problem with doing this is if you have context, it's not specific that it's an allocator, so maybe it's less explicit to do this. But if you wanted to have it like be as less annoying as possible, you could use context and put all the functions of print and free inside it. But it's less explicit to do this. So using like a context struct like this probably does go against the style guide a bit, because say for example if a function in Zig does something like, say, like this, you see, oh, there's an allocator here, therefore, oh, this allocates memory, or it could allocate memory, and it probably returns an error. So it's kind of explicit when something allocates memory, which is, you know, kind of the philosophy in Zig. Whereas if you just put context, do you know if it's going to allocate? Probably not. So I would only use the context if you just want to be kind of, if you just want to make things simple but not be as explicit. But it is kind of going against the Zig style a bit. All right, so now I'm going to go through logging. So logging is another way of printing, and it's actually pretty useful because you don't need to import the writer or anything like that. It just generally works. So first I'm importing log. So log std.log, just because I don't want to write std dot all the time. Then we have this options file, which I'll show you later. But you have 4 options generally. So if you just type in log dot, we have debug, we have error, we have info, and we have warn. In Windows, it doesn't show me in color. In theory, it should. I say warning, like so. So here I just got some random debug information. I think I'm running this. I am logging. So this will basically create a value. It will print the value, and it will say warn if it's over 50, error if it's over 200, and then debug. I'll just print this. So here, warning. Yeah, we probably shouldn't say warning because it does actually say warning. Oh no, test. The info value is 0, warning value over 50, 100, warning test. So we also have debug here, and you see that the debug isn't actually printing. And that's because of this setting here. So we have std options, which is the log level, which is basically the base level you want. So if you're in like a debug build or something like this, make this debug, which is actually very useful. So now the debug will show you the value. So what you could do, in theory, you could fill one of your functions with loads of debug information, like debug, log.debug, which I'll show you. So you could do like, let's replace this with debug, and then let's replace this with debug, and then let's replace this with debug, and just say log info end, something like this. And then maybe we could, I don't know, do something else like value minus equals 5 or something, and then we can log debug that. Say run debug now. So we'll see a lot more debug information now. You see we have debug value 0, debug value 1, 100, debug, well, warning 100, debug value 150, debug 145. And then we can change this to info. Save it again, rerun it, and now all the debug information is gone. So you can use it kind of like a debugger when you actually want to fix bugs, but then not have it in production code like this. So logging is extremely useful for that reason. Alright, so that's console input and output with the new system. So this could change in the future. That's how it is in 0.15 anyway. So I think that's all for this tutorial. I didn't cover literally everything. There's things like importing C files, maybe making libraries, maybe importing other Zig libraries. That involves using the build system. But this is basically just a tutorial on Zig itself, and this should be enough for you to get started. So let me know if you have any questions, and thanks for watching this really long tutorial.